Well, thank you very much for attending this tutorial. My name is Ameen Abu-Hanna, and I'm very pleased to provide you information about prediction models in medicine. Let me share my presentation with you. Again, I'm very pleased to provide you or offer you this tutorial on evaluating prediction models in medicine. A very short background about myself. Uh, I have a BSc in computer engineering, a master in computer science, and a PhD in AI. But since 1997, I'm at the Department of Medical Informatics in Amsterdam, and all the projects we work with involves clinicians, general practitioners, and very related to medicine. Practicalities. So I will try to have the format of speaking for 45 minutes and then take a 15 minutes break. So we have this 4 times. Please ask questions during the talk. Just open your mic and interrupt me, and I'll just take care that it doesn't take too much. If I feel that it will take too much time, I'll defer the question for the end. But I will also make sure that I pause from time to time and just ask if things are clear. We already tackled the recording of the tutorial. So let's see if this works. I have a lot of material, but the idea is to really convey the most essential parts of prediction models and about how to evaluate them. I think a year ago, I recorded some tutorials. It's a 4-part tutorial on prediction models, and it is on YouTube, but it is unlisted. I can share the URL with you later, so only people with the URL can watch them. And the presentation today is an extended version of that, but the essence is already in the videos there. But I have much more material today. So I'll give a general introduction. Then the 2 most important parts will be about performance measures, like how do we know if a model is good, how to measure the goodness of the model. And then we can see that we can use these performance measures for selecting the best model and for validating it. And I'll end with related topics. For example, more about causality, about other types of problems that we deal with, missing values, and the like. So first, what is a medical prediction model? So a medical prediction model is a tool to provide risk estimates. And there are 2 types of prediction models. One is a diagnostic prediction model, and the other is prognostic. So when we talk about diagnosis, we're talking about the presence of disease at the time that we're giving the prediction. So for example, the GP, general practitioner, has a visit from the patient, and the GP wants to decide if the patient has a disease already at that moment. That's diagnosis. Prognosis is you want to predict something that will happen in the future. And it may concern the natural history of the disease if you don't do anything, or if you do treatment. We don't mind. In both of them, we talk about prognosis. Many of my examples will be prognostic in nature, but the 2 have the same kind of basis. So all the concepts we will deal with are related to both of them. An example, I'm sure you all have an idea what the prediction model looks like, but there's a lot of risk calculators, for example, on internet. So this is a tool that estimates my risk for 10 years from now to have a heart attack. These are fictitious numbers. I'm older than this now. So if I put some information here, so the system is asking me about some values of my variables, and then I click and say, okay, calculate my 10-year risk. Then it comes back and says, okay, you have a 3% risk. And for today, I would like that we are equipped with tools and concepts to understand what does that mean, 3%. Do I trust it? Can I act on it? And so forth. But before I start, I really want to make like a framework for us, because there's a lot of literature out there and it is sometimes difficult to understand. Are we doing a prediction model? Are we doing a prognostic factor research study? Or are we talking about causality? So let's just take a minute and please ask if it's not clear. So when we talk about prediction model, we're talking about a tool that is aimed to predict the outcome. It's a kind, in a way, of black box. I don't care. I just care that the outcome is, that the predictions are good. So you would see in a paper, for example, our prediction model had an AUC of such and such. So the focus is on the box itself and what comes out of it. When we talk about prognostic factor research, at this kind of studies, you're aiming at identifying predictors that are associated with the outcome. So it's really about the predictors that you're interested in the predictors. So a paper can end with, we found that BMI, body mass index, is associated with mortality. Or we found that BMI is independently associated to mortality when adjusting to age and sex. So what's important here is that you have a factor or a variable that is associated with an outcome, and it's only associated. It doesn't mean that it's a cause for it. You can also correct for some other variables. And when I say correct, just think about stratifying, like having the same age and sex, and just look at the BMI in each of these strata. So even when I correct for age and sex, the BMI is still independently associated, but still it's not causally related to it. If we go another step, and then you can see that some studies want to know if there's a causal relationship between a variable and the outcome. And the aim here is to investigate whether if I change the variable, that the outcome also will change. In these studies here, it doesn't mean, when I look at prognostic factor research, it doesn't mean that if I change the BMI, that the outcome will change. It's just that there's an association. When we talk about causality, we really talk about that something affects the, not just associated with the outcome. So you could see, for example, a paper saying, we found that benzos, the usage of these medications, was causally related to falls. In that case, we have to find an independent association between what you want to study and the outcome, but you have to correct for very specific kind of variables. Those we call confounding, and those we call risk factors. Just a very short example. Suppose that you do a study and you find a variable is a very strong predictor of outcome, and you look at this variable and it says, for example, that somebody was admitted to hospital recently, and this is very strongly associated with a bad outcome. It doesn't mean that if you prevent people from going to hospital that they will have a better outcome. It just means that those who went to the hospital were already were severely ill. So that's what we call a confounder. I'll talk later at the end of the tutorial more about causality and about the specific study. But keep in mind that we have different ways to the different related topics when we talk about prediction models. And so prognostic factor research can lead at the end to causal inference if you do it correctly. But the focus of today is on prediction models. So we're just interested in providing estimates, risk estimates of an outcome. And we want to know how good these are. Other questions about this slide? I can imagine it could be a bit confusing, but the focus here is about the tool. I look at the tool and what it provides me. Prognostic factor research is interested in things that affect, I'm interested in the predictors themselves. And if I go to the causal inference, I'm interested in predictors that are even not just associated with the outcome, but they are causing it. Okay, so I hope this is clear. So let's just take a moment and see, when we look at prediction models, we're talking about learning them. It's called supervised learning. So we have a data set, we have a learning algorithm, and it can result in different kinds of models, right? So I have a learning algorithm, I can learn a linear model, logistic regression model, decision tree, neural network, They're all in the realm of supervised learning. And why it's called supervised, of course, because we know I am supervising the algorithm to predict a specific outcome. So I say learn mortality and predict mortality based on the other variables. And these models, they can have different forms. So they can be regression models, support vector machines, whatever. They get inputs, and they can be binary, categorical, numeric variables, and the outcome can be also binary or multi-class or numeric. For today, we will focus only on binary outcomes. And more specifically, we will focus on probabilistic classification. So we're talking about applications or models that predict the probability of a class, because most applications, as we will see, will require models that predict the probability of an outcome rather than a 0-1 outcome. And this is called probabilistic classification. And most classifications, the good news is that if you do decision trees or support vector machines or other models, it's quite easy to translate their outcome into a probability. One of the most used tools in medicine is logistic regression. So it's a statistical tool that talks in probabilistic terms already. So let's just take a second and look at it. So this is a logistic regression model. It's just getting in with one variable. So you give me here severity of illness of a patient, and you ask me what's the probability of the patient to die given some severity. So it's a very simple formula. You plug the S here in the formula. If the S is very large, this will lead to about 0. This will go to 0, and the whole term will approach 1, because it will be 1 divided by 1 plus 0. And if S is very negative, this would be a huge number, and it will be 1 divided by a very large number, which is approaching 0. So you see, it is a nice term that is always between 0 and 1. The higher the severity, the higher the probability of death. And of course, it is not useful if you just have one variable. You can also put what we call the linear predictor here. You can plug in different variables in the models, age, sex, and other variables. So you first calculate what we call a linear predictor, and then you plug it in the logistic formula here, and I get a probability between 0 and 1. Let's take a moment to appreciate what we can do with such a model, just to have a feeling. So this is one neuron. I assume everybody knows what a neuron is, but basically one neuron is just the same as a logistic regression model, assuming that the activation function is a sigmoid. So what does logistic regression do, or one neuron? And we take it just with one variable, age, and I have two parameters of the model, beta 0, beta 1. And first I calculate the linear predictor, beta 0 plus beta 1 multiplied by age, and I plug it in this formula, and exactly like we saw before, I get a probability. I just want to show you how flexible this model is, or limited. So if I increase the beta 1 here, I can get steeper and steeper S-shaped forms. If I put a negative beta, I can flip the form. So I can also model things that where the probability goes down when the variable or the linear predictor goes up. I can do more. I can play with the beta 0. When I make it more positive, the S form goes to the left, and when I make it more negative, it goes to the right. So I can play a little bit with it. But it's extremely, so it's a parametric model. I give you the form beforehand. I know everything, the variables, the formula. And the only thing I want is to find the beta 1 and beta 0 that have a desired outcome. That will be the learning part, right? So let me just show you what we can do with that. So I go back to here. So I'm going to take this neuron, I'm going to copy it. So I copy it one time, so I have twice. And the only thing I change, I put beta 1, 5, just an arbitrary number. and here 5, and I change the beta 0. This has a 0, and this has a -3. And I'll force the age to be standardized between 0 and 1. You can always do that. And then as before, well, I look at what comes out, and you see it's still the S form. It's continuing like this, but I'm cropping it because I have the age only between 0 and 1. I get this form. For now, it doesn't matter exactly. I just want to show you how you can get arbitrarily complex models. So this neuron produces this form. This one produces this form. I can go another step ahead. I can take this output multiplied by -1, which will flip the outcome. I multiply this one with half. It will scale it. And then I add them again. But now I take just a linear outcome. I don't do sigmoid. And I can get something more complex. So the idea here is that with very simple tools like logistic regression, you can have, if you do multiple layers, you can get really crazy shapes, and you can fit whatever you like. It can be handwritten things, it can be an MRI image, and so forth. So okay, so we get the feeling of what these models can do. But let's go back to the main idea. Why do we want to predict? Why do you want to have diagnosis or to predict something in the future? So there are really 3 basic reasons. One, if we are in the realm of public health, so we are not ill yet, and we're talking about prevention when we talk about public health. So here we're talking about the need to identify high-risk people to have an adverse outcome. Why do we want to do that? Because we can have preventive actions. For example, we can look at a high risk of older people to fall, and we can provide them with exercise training. In clinical practice, so we are already, we talk about patients, people are ill. We can talk about risk of having a disease at that moment. So it's a diagnostic tool in that case. And why we want to do it? Because we can ask, okay, is it a high risk for having a disease? I can start the intervention now. So it looks a little bit like the first one, but here it is for something that happened in the future, and here is something that is now happening, and it's diagnostic. And when you see this, it means that the next slide is will elaborate a little bit on this point. Another reason why we want to predict something, especially in this case in the future, is because we want to inform patients and families. For example, in the intensive care unit, some patients are so ill that, they are also sedated, you have no contact with them, they're so severely ill, you can continue treating them, but they are actually, maybe it's a futile care, nothing will happen, nothing will improve. And if you just keep them there, it's not good for the patient, it's not nice for the families, and you're also occupying a bed that somebody else could use it and benefit from it. So it could be used, for example, for supporting discussions about maybe withdrawing therapy. So informing patients and families is an important reason why we predict. Another reason is, if I make a prediction of something, and I say, okay, what would happen under circumstance A and under circumstance B, and I can compare the outcomes in order to inform my treatment selection. I would say, oh, I'll do B because B will have the best probability of a good outcome. Another domain why we want to predict is in clinical trials, in research. For example, in clinical trials, you would say, I want only to include very severely ill patients. So what does that mean? You can translate it and say, okay, if my model will predict that the outcome is above 80%, then I include you in the trial, and then I randomize you. For half of the patients, you give the treatment, and you maybe experimental treatment, and the other half you give a treatment as usual. But at least you ask the model whether a patient is eligible to be included in the trial. So this is an example. So I go back for a second. We're talking about risk of having a disease. So this is a slide I took from the Odyssey work. So you have a clinician, and then you have a patient visiting the clinician, and then this is so here you have different outcomes of estimate that you want to predict. This is the story of the patient. These are our variables that we want to include as inputs. Here we have a population average of our outcomes, suicidal thoughts and behaviors. Normal is 3%. For this specific patient, the model says it's 14.6. And this is very high compared to the population average. And the other things are not very different than average. So you can say, okay, I'm going to now intervene on this prediction, and I'm going to offer the patient, for example, a specific therapy. Okay, let's take a moment and look at the life cycle of a prediction model. So there are different ways to look at it, but one is looking at the software engineering life cycle, where you have requirements. So in our case, it will be establishing the outcome of interest, what you want to predict, and selecting possible predictors. In the design phase, you choose appropriate modeling techniques. For example, you say, I'm going to use a neural network or a logistic regression or a decision tree. Then you develop your model by fitting it, and there will be also some model selection. We'll talk about that. An important part is, okay, you have a model now. How good is it? That's called validation. An important part where much research does not get there, but is really at the end, the reason we do this model is putting into use, like deciding on starting therapy or doing something with the model. And so the focus of the tutorial will be on these two steps, because we were going to use performance measures, how good the model is, evaluate the model, in order to decide on the best model, so model selection, and also to say how good the model is if I've used it on a new data set, validation. Any general questions about the introduction up till now? No? Okay. So let's go to the meaty stuff, performance measures. So the question is, you gave me a model, and I need to know how good it is. So what is goodness? And the question of goodness and I use the word forecast here instead of prediction just in this slide, because it's coming from weather forecasting, and there's a lot of rich literature about it, because these guys, the whole business is to predict the weather. So Murphy described three kinds of, when we talk about goodness, what do we mean? One is called consistency. So if you want to predict or give a forecast, I assume that your forecast will be corresponding to what you really believe. You're not going to hedge, what we call. And this could be even a reason why probabilistic prediction models are better than models that give 0 and 1, because they are not consistent in the sense of, we all know that when you give a prediction, it's never 0 or 1. It's a probability. It could be very high, could be very low, but it's always a probability. But anyway, so I expect you to be consistent. The other part is called quality, and this is the most important part for today. It is, I'm going to check your predictions and match them to the outcomes, to the observation, and see how good they correspond to each other. And the last one is value. If you put it into use, does it have economic value or improvement of the patient's outcome, and so forth. The most technical part is this one, the quality. So we're going to talk about it. So it has the statistical properties that we want. We're going to check how good the outcome corresponds to our predictions. So let's start with a simple example. We have a data set. I ask your model to give me predictions. For now, let's suppose that this is a test set. Let's not get bugged into the details now, but suppose I have a new data set, and you told me you have a model. I ask you, okay, predict for this female of 27 years old, what her chance is, for example, for a bad outcome. And I'm sorry, I'll be talking a lot about mortality in this tutorial because it's easy to convey. So what's the chance of the first patient to die? Is 20%, 60% for the second one, and so forth. And I have the truth. I know what happened to them. If I wait in a follow-up, or maybe I know it already, I have the 0, 1, 0. So this patient did not die. I expected 0.2. And this I expected to die, I have 60%, and so forth. And it is amazing how many ways, only these two columns that you have, you can analyze them in very many ways. You could analyze them at the individual level, comparing 0.2 with 0, or combining them into groups. And there's a lot of ways to look at it. For now, I just want to show you a very simple way to start looking qualitatively at what's happening. So just take all the patients who lived together, just combine them together, take the subgroup of those who died, and just let's plot their densities on a plot. So here, all those patients lived and also the patient who died. Now this is density. That's why it can be more above 1. It's not a probability, it's a density. If I want a probability, I need to specify a range, and then I have to integrate. So I have to find the area. Area under any range will give you the probability for the patient to be in that place. So just by looking at it, what we hope is that the green density will be to the left. These are the predicted probabilities, right? So for those who lived, I hope that my model will give them very low probabilities to die. So remember, all the time when we're talking about the predictions, we talk about predictions for the outcome. For those who lived, I hope that my model will push them to the left, and those who died to push them to the right, to the 1. And now let's talk about 2 fundamental aspects. So here it is just qualitatively, just understanding what we want, just looking at this graph, and we try now to formalize things. So there are 2 fundamental aspects in performance measures of prediction models. One is called discrimination, and one is called calibration. So discrimination is really about how able your model to provide higher probabilities to those who died than those who lived. So that's the discrimination part. You have those who died, those who lived, and you ask, give me the probabilities of dying for these patients. You hope for those who died that the probability will be higher. That's discrimination. So are you giving, in general, higher probabilities for those who had the event than those who didn't have? And we're going to measure it. We're going to quantify it. Calibration is really different. An important thing that's usually, or not, well, it's getting more attention now, fortunately. And it is really when you give me a prediction. Remember the model I showed you at the beginning that gave me a prediction of 3% of having a heart attack within 10 years. I just want to know, is it the real probability? You gave me 3%. Is it really, does it correspond with the true probabilities? But you can tell me, how do you get these true probabilities? I'm generating the model in order to predict them. Yes, so with our ways, we could try to estimate the true probabilities based on a test set. But the concept of calibration is the correspondence between the probability that you gave me and the true probability. Discrimination is about outcomes, those who lived and those who died, and I'm comparing if my model is giving more probability to those who died. So let's talk more about discrimination now, and we look at 3 measures. One is called the discrimination slope, and one is the area under the AUC. It's the area under the curve, and the net reclassification improvement. So the discrimination slope is extremely simple. Remember the density plot that we had, those who lived and those who died. I just take the means of those who, so the predicted probabilities for those who lived, I take their mean, I take the mean of those who died, and I just calculate the difference. This is the discrimination slope. Why is it called slope? Because I can plot it differently. I can make box plots. So I take all those who lived here, all those who died here, and don't worry, our plot is still relevant. Just instead of a density plot, I make a box plot. So this corresponds to this one, this corresponds to this one. And slope, because this is the rise from this mean to this mean, and because the run is from 0 to 1. So in a way, it's kind of slope. It's this divided by this. But it's just exactly the same, the difference between the means, the predicted means. The area under the rock, I assume that most of you are relevant or acquainted to it. So I will be a bit quick, but I'll just review it. So let's talk about the rock curve. It is the most used and abused measure in predictive modeling. So let's go back to our 2 columns, the predicted probabilities of dying and the real outcome. And now I'm going to force these predictions to become, to binarize them. I'm going to binarize them, that become 0 or 1. So for example, if my threshold is half, everybody about half will be, under half will be 0, and above half will be 1. So now I have two different columns. One is the predicted, so if you see y hat, it means the predicted outcome, the binary outcome, and this is the true outcome. Now, every time you see two columns or two variables which are binary, the first automatic things to do is to do a 2x2 table. And you just organize the times that both of them were 1. So this is the truth was 1, and the prediction also when I force it to be 1 or 0. If it was 1, I count here how many times it corresponded to the true predictions of 1. Here, the true negatives are the times that the model said, I predict that the patient will live, and it truly lived. And here, on this diagonal, we have the false. The system thinks it's positive, but it's not true. So the system thinks they will die, but they did not die. And here, the other way around. And okay, so what can we do with that? We can now make different estimates from this 2x2 table. And I will go here very fast. I can calculate the errors. So on this diagonal, it's the number of errors. And then I can divide by the number of cases. And the example is very simple. I can talk about sensitivity. Here in sensitivity, I'm interested in the patients who died, so with the event, and I'm going to ask how many of them did you catch? So the model caught only 1 from the 3. So when we talk about sensitivity, and I know some people from information retrieval, they call it recall, it's the same, but in medicine we call it sensitivity. So sensitivity is how many of the events were you sensitive for? How many did you catch? I caught only 1 from 3. So that would be my sensitivity. And I actually prefer this kind of notations. It's the conditional probability. Given that my patient died, only in them I'm going to count how many did you say that, the proportion of them that you also thought that they will die. Specificity is analogous. We're talking about those who lived and asking how many of them did you catch correctly. And important thing is to understand that sensitivity and specificity are at odds. So the higher the sensitivity, the lower specificity. And how to see that? Well, imagine that your model says, you know what, I think everybody will die. You're 100% sensitive because those who died, you caught them. But you're 0 specific. Why? Because you didn't catch anybody who lived. And the other way I can say, my prediction is that everybody would live. In that case, I'm 0 sensitive. I didn't catch even 1 person who died. So sensitivity is 0, but I'm very specific, excellent, specific, 100% specific, because those who lived, I caught all of them. So you see where we are going, which direction we're going to. And if you look at sensitivity in terms of the graph we saw at the beginning, the figure, we're talking about those who died. So I'm only counting in those in the red zone. If I take a threshold, I look at this area. I'll just use the pen for a second, see if it works. Yeah, so I will look at, okay. Yeah, now it is, sorry for that, I go back. Yeah, so I'm counting in this area, I'm counting how many did I catch from the whole, including also those. So it is this part 1 that I caught, because this was my threshold. Everything above here, I say they died, and I caught this part 1, and I divide by 1 plus 2. Okay. And I go back from the pen to, yeah. And you see, if the threshold is higher, I catch a smaller proportion of the patient who died. This is an important concept, the positive predictive value, which is called precision in information retrieval. And the starting point is not what the truth is, but what the model thinks. So I start with, you said, okay, how many patients you you predicted to die, and I divide by the ones you made predictions of dying. So how many truly died from those that you predicted? Let me just show you how it looks like in the graph. So if this is my threshold, now I don't look at the whole red zone, I look at anything in the box, the green and the red ones. And I say, okay, my predictions that those all of them died here in the box, and my mistake will be, of course, the green part. So I will say it will be the part of the red that I capture divided by this part of green plus the red part that I code. The problem with the PPV is that if I move my threshold here, right, I can get a very, very high PPV, which is good, because from those you predict how many really died, is very, very nice property. But just remember that maybe I'm talking about a very small group. Maybe I'm talking only about 10 patients. So I have maybe 99 or 90% PPV, positive predictive value, but for a very small group of patients. And we'll talk about later about the interplay between sensitivity and positive predictive value. Okay, just let me see the time. Let's take the ROC analysis, finish it, and then I ask for questions. So the ROC analysis is now, the tools that we learned now, we can use them for the ROC analysis, receiver operating characteristic. So what we've seen up till now, I took one cutoff point, and I made this confusion matrix, and then I could calculate all these things that I showed you. But I can aggregate this these measures by saying, okay, let's do this cutoff points continuously from 0 to 1, and every time I take a different threshold, I calculate this confusion matrix, and then I will take two specific things from it, and let me show you. So these two things that I want to calculate is sensitivity, how many patients who died you really captured, and specificity, how many patients that lived did you also capture in the predictions. And then we're gonna plot sensitivity versus 1 minus specificity. It's just a custom to use this measure. You could also put specificity, you get a bit different graph, but this is the common way to do it. So now we're gonna go back to, this is the truth, the Y01, and this is our prediction. And then I can say with a threshold of 0, if I say everybody from 0 and up will die according to my prediction, then your prediction will be everywhere 1. I predict all the predictions will be 0 or above. So I expect everybody to die. If I add a bit to the threshold, for example, it is 15%, this person will not be predicted as dying. So it will be 0, and all the rest will be 1. I sorted the predictions from low to high. So you will see what will happen if you continue with that. The 1s will be pushed down and the 0s up, just by ordering the threshold. Okay, so if we take for every column and we calculate the this confusion matrix 2 by 2 table and calculate sensitivity and specificity, I will get as much sensitivity and specificities for as my columns here, as my thresholds. And then I can just plot them. So each point here, so this is the ROC curve, and each point on it corresponds to one threshold with 2 numbers, the sensitivity and 1 minus specificity here. So if I look at this point, this is exactly the point with the threshold of 0. If you say everybody will die according to your model, then you are 100% sensitive because you caught all of those who really died. And at this point is the other way around. You said everybody will live according to my model, and your sensitivity is 0 because you caught none who died. But the specificity will be exactly the other way around. Here it will be 1 minus specific will be 1. I'll be 0 specific here, and I'll be 100% specific here, which is 1 minus specificity will be 0. Okay, so if you do this graph, you hope that you'll get a little bit closer to this point where you have a perfect model, 100% sensitivity, 100% specificity. I've never seen such a model in my life with a real data set. And then if you do this thing, you plot it, then the AUC is the area under this curve, and it's a measure that we use about for discrimination. And why it is a measure of discrimination? Because it turns out that this area is exactly the thing that you would get if you do this trick. You take all those who died apart in one group, all who lived in another group, and now you will pair them together. I'll show you in the next slide how we do it. And the proportion of pairs which are correctly ordered will be exactly the AUC. How does this look like? This is very easy. So suppose I have 3 patients who died and 2 patients who lived. So now I'm going to have all so these patients, and sorry for my metaphoric use of language. So these who are going to meet, everyone who died will meet everybody, anyone who lived. So this person can meet these 2. I compare them with these 2, this one with these 2, and this one with these 2. So I have 6 combinations. And now we're going to do a table for all the combinations. I'm going to take the pair. So the first patient who died with the first patient who lived, it was 0.6 versus 0.3. And the only question I ask here is whether the probability of the person who died had a higher probability. And I would like the model to have this ability, because I'm predicting here, all these predictions are predictions of dying. So also for those who live, this prediction, they're 30% to die, 65% to die, here 60% to die, and so forth. So in this pair, the model did the right thing. It gave the person who died a higher probability to die. So I say it's a win here. The second combination didn't go well, because the person who died got a lower probability to die than the person who lived. So it said, okay, you get a 0, so you get a kind of penalty, and so forth. So you see in all these combinations, from the 6, 5 times this experiment succeeded. And then you could just say the AUC is 5 divided by 6. So this is the interpretation of the AUC in terms of pairing, and this gives you also why it's a discrimination, because we're looking, discrimination is about the ability of the model to give higher probability to the person who died than the person who lived. So this is the AUC. I hope it's clear. And let's finish with an example. And that's nice, because with the tools that we learned now, just by showing you this, you can now calculate the AUC for these. How many do I have? 30. I have 40 patients here. Every point, every number here, for 0 or 1, is a patient. And I sorted their predictions from the lowest to the highest. You don't see the predictions, but they are sorted. So this patient here lived, and he or she had probabilities higher than the ones on the left and lower than anybody on the right-hand side. And if I ask you now, what is the AUC, just looking at this? So let's see. Let's use the approach that we just did with meeting. So these 10 people who died, gonna meet, each one of them gonna meet anybody, every one of the patient who lived. So it's easier because it's a smaller group, only 10 that died, luckily. We're gonna pair them with, so I'm gonna take this one, this person, and pair with all the green ones. So if I take this person and I do the pairing with all these 25 patients on the left side, what do I conclude? These 25 experiments will be a win in all cases, because by definition, this one was higher than all these ones. Remember, when you pair it, the only question I asked you, did the person who died have a higher probability than those who lived? Yes, for all these 25. So I have, for this one, I have 25 ones, 25 wins. For this one, the same. For this one, the same. For this one, the same. Now, when I pair any of these 4 with those on the right-hand side who lived, I don't get any points, because those ones got higher probability to die than those ones that really died. So again, for this person, I'll get 25 points, and 0 from these ones. For this one also 25, 25, 25 points. When I go to these guys, the 6 last ones, I see, okay, so how many combinations I can have? I can have also, again, 30 combinations with those who lived. We don't compare ones with ones, right? Because we put all the ones together and all the zeros together. But I can compare this one with all 30, and I will win in all of them because the one was on the right-hand side of all these who lived on the left-hand side, and I do it, I have 6 times. So in short, the AUC will be 25 times 4, because each one of these 4s won 25. And from these last 6, I had 30 wins. So 6 multiplied by 30, and I divide by the number of combinations I have. How many combinations? 10 multiplied by 30. 10 died and 30 lived. So that's the AUC, just by looking at this ordering of patients and looking at this game of meeting. Are there any questions at this moment before we go to break?
I would like to ask one, more of a curiosity.
Sure.
When you were talking about the threshold,
Yes.
normally, do you have like one that you normally choose, or do you aim at some of them, or do you normally like run all and choose the best cutoff for the problem that you are dealing with?
Yeah, excellent question. For now, what we learned is that I don't choose anyone because I want an aggregate estimate.
Okay.
And it's better that if you want to choose, there are different ways. So one way is using something called the Uden index, W-O-U-D-E-N. And the Uden index is something that tries to find the point that is closest to this perfect model. So in this case, I'll try with it will be a point here. So it will be a point to choose this one.
Okay.
But in medicine, this assumes that you don't care about sensitivity, you know that you don't give them the same weight. But in medicine, we usually have costs. And often, for example, in public health, sometimes you think, I want to capture more patients. I don't mind that. I want a good sensitivity. I want to capture those who are likely to be ill in the future. And I don't care if I give them, for example, an exercise, for elderly people. It's okay. I want to find those. So in that case, I will give sensitivity more weight than specificity. And I will be leaning to points up here. So I will have more, I will go to the right-hand side. So it really depends on the thing that is, then we're talking more about value in the terms of Murphy. So we have quality, this is quality. But so we have to infuse some cost into it to make it more suitable to your problem. Is that does that answer your question?
Thank you.
Okay. Any other questions at this
yes,
moment?
I mean, I have a question about when you defined the discrimination power, you defined it as the difference between the means. Is it always like that, or
no, this is one measure.
Use also medians, for example, if the distributions are skewed.
You have medians if you want. So that would be a different measure. So here you can, the nice thing here, we can just sit and think whatever we like. We have this, sorry, I go back to the slide because it's very, so this slide is going to come back here. So you can say why to take the mean, because the mean can be biased by, it's just one measure. You could take a median also. It would be a different measure, and you can call it something different. But you're right. We can define it whatever. You can take different quartile. You can say I want a different quantile to compare it. It's just one. I'm just showing examples of measures. I usually use the discrimination slope and the AUC, but there are also other approaches. Let's just summarize the two measures that we discussed before of discrimination. The AUC is also called, well, it's another measure called concordance statistic. It's exactly the same measure in terms of value. Well, the calculation, as I showed you before, they are use rank order statistic, like you have this these meetings, and you see if you win or lose. And by the way, if the probabilities are exactly the same in a meeting between somebody who died and somebody who lived, then we give half a point. The pros, it is insensitive to outcome incidents. Sometimes can be actually a problem, but in general, the AUC is robust to the incidents. It is interpretable for pairs that we saw, and the cons is that the interpretation is a bit artificial. The discrimination slope that we discussed first, it's the calculation is just the difference in the means of the predictions between the outcomes. The visualization is a box plot. The pros is easy interpretation and visualization, but it depends on the incidence of the outcome. Okay, let's talk about something called the net reclassification improvement. And historically, if people became excited about finding all kinds of new biomarkers, and you hope that these biomarkers will make the models better, for example, diagnostic models, but also prediction model in the future, prognostic models. And the thing that you found is that usually, you're quite sure that your biomarker is doing something, but it was hard to move the AUC up. So this is a measure which is a bit more sensitive to that, to the improvement. But it has also some drawbacks. But it gives you some insight. If you have two models, you have one model without the biomarker, and then you say, okay, now I'm going to add another variable to it. And you're going to see, well, how well is it doing better? You could try the AUC, you could try all the other things that we'll learn today. But one simple way is just to check. Let's see, we again divide our population between those who died and those who lived, the study population. And then for those who died, what you hope is that the new model with the biomarker, for example, is giving higher prediction than the old model because the patient died. So you hope actually the prediction would be 1. And for those who lived, you hope that your new model with the biomarker will have even lower probability for dying for those who lived. So in other terms, if we go back to our graph here, we hope that the new model is pushing the green area to the left and the red area to the right. So that's the net reclassification improvement. So sometimes you see papers reporting it. And it's always not just to see, just to check, are we moving to the right direction? Now I would like to ask you something. Now suppose there's an oracle and it's giving you the right, the correct probabilities of outcome. It doesn't have to be that, but to make it, clear that there's something strange here. So suppose you really have a column of the right, the right probabilities for each patient. And then you do the calculation of the AUC. And now suppose some malicious person comes to your computer and squares all the predictions that you made. So predictions that was half, it becomes now quarter. So all the predictions will be messed up. They will not be the true ones. Now you recalculate the AUC of these bad predictions, and the AUC, does anybody would like to say what you think? What happens to the AUC?
It should be the same.
Would be the same. Exactly. It does not change. And this is really strange, right? Because we had the true ones, and now we're doing something to it bad, and then it doesn't say, it's not complaining the AUC. So let's see why that is. I hope that just by looking at this example that we saw before, that it gives you the answer. Because now what happened to the probabilities? Okay, I maybe have to stress that this change, when we squared, for example, it's monotonic. So if it's the order does not change of the probabilities. I'm not giving a strange transformation, just a transformation that keeps the order, but I'm just pushing them. So if I look at this order, the predicted probability, they all will move to the left, but all the patients also move to the left. So there's nothing changing here. So if the probability of this person was half, Now it's 0.25. But this one will get even also smaller one. They all will be pushed to the left, but the relative order will be the same and the AUC does not change. I hope this is an illustration that explains why the AUC does not change. Another simple example. What's the AUC here? Can anybody tell me? So we have here class 0 and class 1. And there's no overlap between them. Anybody would like to say what the AUC is in this case?
I think 1.
Yes, exact. So we see 1 because if we look at this combination of the two subgroups, in any pair, the red one will win. So we have all the pairs that win. Now, if I just move this here, the AUC is still 1. So you see, it's not sensitive to the probabilities. It's just a measure of discrimination, but it doesn't tell me the whole story. So we will see there are problems. The AUC is not telling me if the predicted probabilities are correct or not, just telling me, are you in general discriminating between these two groups? So it's giving something about the potential of the model. It's not telling me if I'm using that potential yet. So now we can talk about something called proper rules or not, or proper measures. So you have non-strictly proper measures, which mean, and the AUC is one of them, it's a proper, but it's non-strictly proper. So it will give me the minimum error, the best value, when you give the true probabilities, but also with other predictions. So I could move the probabilities and still give the same AUC. The strictly proper measures, we didn't talk about them yet, will give you the minimum error or the best performance only when the predictions are true. So if you give the true probabilities, it will give you, okay, now I have the minimum error. But if you're gonna mess with them, like square them, they will scream. They will say, no, it's becoming worse. We have even non-proper measures, by the way, that don't even have these properties. Observations. The non-strictly proper are like the error rate, like the AUC, like the NRI. They're non-strictly proper. I can play with the predictions and still get the same answer. Strictly proper, we will meet them later. But the nice thing about the AUC and NRI, at least, they have this intuitive meaning that we've seen before. So from the measures that we looked at up to now, they are nicely interpretable. Now, there's another problem with the AUC, is that when the prevalence is very low, so for example, you have only 1% mortality or 0.5% mortality in the data set, the AUC can a bit be misleading. You will get maybe a good AUC, but when you want to use something, the model in the clinic practice, I don't only care about the AUC, I want also to know what will be my positive predictive value. Remember, the PPV is from those I predict to die, how many died. So if I predict 1 million patients to die, but only 2 of them died, my PPV is really, really bad. The PPV decreases when the prevalence is low. That's the problem with it. Let me show you an example. So let's go back. Let me see. Yeah. So the problem will be pronounced when this tail here in the tail of the green part, we are gonna have more and more green points. So we have a fat tail here. And let me just illustrate it by the example that we've seen already. So remember this example, we put 25 who lived, 4 who died, and 5 higher. So the probability is still going up from left to right. But now I'm gonna look, but first I should say, I'm gonna look at some properties. If I put the threshold at the A point, so everybody above this probability, I don't show the probability here, but everybody to my right will be predicted to die. What will happen? So my PPV will be 10 from 15. So I predict here from these 15 page 6 plus 4, 10 plus 5, 15. So I count by 15, only those I predicted to die, and I caught 10 of them. My sensitivity is 100% because I caught everybody who died, but my positive predictive value is 10 from 15 because I missed these 5. Now, if I go to the B, you see now I will catch less. So you see that sensitivity will be less because I will catch less patients. And the PPV will be also changing. It doesn't matter. What I want to show you is, let me do something now else. I'm going to start with the same example we had, but I'm going to infuse a lot of zeros here and here at the beginning. So now instead of 25 patients, I have 2,500 patients. So 2,500 patients here. And instead of 5, I'm going to put 500 patients. I'm not going to change the ones who died. So what did I do? I artificially reduced my incidence because now it's very low. I have only 10 patients from so many patients. So let's do the same trick now and take the A and B. Let's take the thresholds here. First thing, the AUC is the same. You just trust me, try it at home. 4 multiplied by 2,500 plus 6 that will win from all these 3,000 on the left side who lived. It will be exactly the same. So nothing changed in the AUC. But if I now look at the PPV, it becomes, if I take it A, it becomes 10 from 510 patients. It's much lower. Now I caught, instead of 10 from 15, let me put you the results that we had before. Let's look at these. Before it was 10 from 15, which is very good, well, relatively good. And here's 10 from 510. It's now becoming bad. So in short, what I'm trying to convey is that the AUC doesn't tell the whole story again, not only in terms of how, if I move a little bit the predictions, but also when the incidence is changing. Sometimes it's nice. I don't want it to be sensitive to, but if I really want to look at clinical applications, I might think, okay, but the PPV now is becoming very low. So don't discard it. It's important, but remember that it could also conceal other information that you need, because these PPVs are very good and these PPVs are very bad. So what to do in this case? So we have this interplay between sensitivity and PPV. And this is called the precision recall plot, which is now used also in deep learning a lot and in machine learning. So they show you the AUC and they also show you this precision recall plot, and they take the AUC, the area under this plot also as a measure. So what does it try to do, this measure? So first, let's see, does it make sense that the form is like this? Okay, if I'm at this stage, this place, and I say, well, everybody will die, I'm very sensitive. I will catch indeed all those who died, but my PPV will be very low in general because I'm suspecting so many people that the true ones in it with low incidence will be very little. That from those I suspect, a very small proportion will be really person who died. If I increase my threshold all the way, I will be less sensitive. I will lose patients who really died, but from those I suspect, my the proportion of those who died will be higher. The PPV will be higher here, and this is the interplay on all the threshold that you can do, just like you did with the AUC. You do it here with all threshold, but now you make a relationship between sensitivity and PPV. And if you take the area under this, it's a measure about the balance between these two things. How much does your model balance the sensitivity with a positive predictive value? So this is a measure that you should know. It's very useful to know. Any questions at this stage about the measures that we've seen? Precision, recall, the problems with the AUC? No. Okay. So
sorry, can I ask
sure,
a question?
Of course, you can always.
Just a small one. As far I know, AUC is like a standard in clinical practice.
Yes.
Maybe precision recall is something new. Is there any convention or any best practice about the size of the imbalance that we have in our data sets in order to forcefully use precision recall and not use AUC, or use both? or there is something, let's see, a limit in which we can ignore precision recall and just use AUC in your data set? I mean, if there is an imbalance of 1 to 10 or 1 to 5, is this imbalance enough to do the precision recall plot?
No, there's no standard.
Mm-hmm.
For me, it's like everybody has their own thing. For many people, they call it imbalance with 30%. For me, I'm very happy with 30%. We work, Tseko years also, he works with data sets with 1%, 2%, you know, like it's extremely, but the convention is use it always. If you want to report it, if it's really interesting, you can report it. There is a convention of what you need to report. And this is called the tripod. I will talk about it later, maybe just in one slide. You have the tripod. This is a reporting standard, what to report on when you write a paper about prediction models. And it says basically you have a measure of discrimination, and usually it's the AUC, and a measure of calibration, we will talk about next. Calibration. I usually add something called the Breyer score to it, which is a mix between these two. And we will see it later. But there's no standard. I think you should, you know, below 10 anyways, use the 10%, use the precision recall. I don't mind to use it anyways, you know, it's easy to calculate, you just do it. Yeah.
Thank you.
Okay. So let me go back to the arrow. Yeah. And now, so now we talked about discrimination. And in the things that we've seen, we always had to force the prediction to become 0 or 1, but we compensated for that because we took many thresholds. But in calibration, we're not asking that question. We're saying, well, why aren't we comparing my predictions directly with the true probability? But you can tell me, where's the true probability? I have just 0 or 1. But let's just first look at the idea. The idea is that there's a true probability. So if I had take 100 patients like the first one, 10% will die. My prediction is 20%. So how do we get this? We have to find a way around it. But the idea is simple. Bypass this Y. Directly look at the predictions, it's a probability, compare it to the true probability. So calibration is about this relationship between them. Let's see how we can do it. So suppose we have a test set. Somebody gives me a test set and tells me, okay, you have a nice model, predict on it. So now I predict, make all the predictions, and I sort them. It's important. I sort them from low to high with their corresponding real outcome. So this patient lived, this patient died, and so forth. So to think about calibration, I'm gonna now do, I need a notion of a group anyways. So one way is keep it simple, and I can go and do it for different groups, but just one of the groups that I can take is, I say, okay, for everybody that you suspected of having a prediction between 10% to 20%, I'm gonna organize them in a group, and I'm gonna do two things. One, I'm gonna take the mean probability. So I take these ones and I take their mean. It is 0.163. And for those, now I have the event, right? I have now the true outcomes. I just take the proportion as my estimate of the probability for this group. And I just compare this number to this number. So we got around the point of having a true probability. This is my estimate by smoothing, by aggregating and averaging the real outcomes. So it looks like this. Now this is the calibration graph we're going to construct. At the x-axis, we have the predicted probabilities of dying, this F1. So I order them. And on the y-axis, I have the proportion that I just showed you how to calculate. So for this group, I take all these patients, 1, 2, 3, 4, 5, 6. I have 6 patients. Their mean was this. Their proportion of death was that. And this is the point. Now, if my model was well calibrated, perfectly calibrated, the F1 will be exactly equal to the observed proportion. So this is the Y is equal to X line, this line. So I hope that my points will be on the line. And I can do this, of course, for all the groups. And there are different ways to do grouping. There's something called the Hosmer-Lemcho that tries to find the calibration. First, they cut the groups in terms of fixed groups from 0 to 0.1, 0.1 to 0.2, and so forth. And they have another statistic, another measure based on quantiles, and specifically mostly deciles. But the whole idea is to take a look at these points and see how far they are from this line. Okay, in practice, if you have a real data set, it would look like this. I'd like to smooth it. I don't like to have 10 points. I like to smooth it. And what we do by smoothing, we usually take a point, for example, around 0.25. If we take this point, this is the ideal line, the red one, and this is the calibration curve that we have, the black one. What we do, we look at a window around this, a window, and we make some smoothing, like taking the mean of the probabilities, which would be this, and taking the mean of the events in that window. I showed you a window of 10, but it's not fixed. It's going to move. Every time I look at any predicted probability, I'm going to make a window around it, and that will be my group. And there are different variants for it, and variants of making the smoother. I like the one called low-S, which takes also the distance. So if I make a group, I trust those who are near me more than those who are far from me. But the idea, I hope it's clear. There's another way, because this is not formalized now, I just show you, and usually it's enough. I usually look at the graph and my eyes tell me something, what's happening. This is for me a sign of what we call overprediction. If it's under the line, it's called overprediction. Because, for example, if I take this point, and let's take 0.5. If I say it's 50%, the truth is a bit lower. So I'm overpredicting. Here I have very little under prediction. It's not a problem at all. I would say this area is a little bit maybe problematic. But if you want to formalize it, there's a way. I'm not going to talk about it, but it's good that you know we have a way to formally test it. Basically, what you take your predictions and you're going to use them so the prediction will be now as a new variable that you're going to fit to predict the true outcomes. And there's a condition, if they're perfectly calibrated, you know something about this new beta 0 and beta 1. It's a logistic regression model. But again, if you have questions, I can answer it later. But I'd like to move forward, just that you know that it can be done. Other measures, I mentioned the Hosmer-Lemcho C statistic and the H statistic. So these are just variant looking at the graph I showed you, taking bins of 10 fixed groups or deciles and calculating the distance, and they have a way to do it. There are problems with those Hosmer-Lemcho statistics, which were pointed out by Hosmer and Lemcho themselves in one paper. They are very sensitive to the sample size, and they're sensitive to where the cutoff points are. Okay. So we looked at measures like the AUC that looked at binarizing the outcome and then comparing that with a Y, with a true outcome. We looked at measures that the calibration that looked at the predictions versus the true predictions. But somebody can say, yeah, but why not compare the predictions with the outcome directly? And that's exactly what scoring rules do. And this is called accuracy. It's different. It's accuracy of probabilistic predictions. It is when you compare individuals between their predictions and their true outcome, and then you aggregate it. So now we're going to do something directly to do it, which is a very intuitive idea, right? It's you predict something, and I know what you predict some probability, and I have the true outcome. Just can compare them to each other. And this is the idea of the Breyer score. I don't know, maybe it's Breyer. If somebody from Germany, you can correct me. I call it always Breyer, but let's stick to that for this talk. So the Breyer score is actually a very simple idea. You take the prediction and you look at the distance between the prediction and the true outcome. And that's it, and you take the mean. So let me show you an example. So if I is 7, so patient 7, and the prediction is 0.3, and the outcome is 1, So what is the error? A Breyer score is a measure of error. The higher, the worse. So then the Breyer score for this patient will be 0.3 minus 1 squared. It would be 0.49, which is quite high. And you can expect it high because the patient died, but I say that the prediction is only 30%. Let's take a patient who lived. So my prediction was 10%, and the patient lived. So it's good. I'm close to 0. And then I just look at the distance squared and 0.01. So this is the Breyer score. Now, the thing that we know about the Breyer score is, of course, that we want a low Breyer score. It's the lower, the better. But the worst highest value depends on the prediction problem at home. So if somebody gives me an AUC, I have an idea, right? This thought experiment of combining, having pairs. Here, I have no idea, is it good or bad? It depends on the problem, it depends on the incidence, it depends on many things. So there's a normalized version of the Breyer score that we call R squared in this context of predictions, or Breyer skill score. Every time you see the word skill, it means we are comparing a model that you have to a reference model, and you can play with the reference model. You can define it differently. So let's look at the most used definition of a reference model in the Breyer skill score. So remember, this is what we had before. I'm gonna leave the n out here, but we see why. What I'm gonna do, I'm gonna take these errors that we described before, the prediction minus the 2 outcomes square, but I'm gonna divide this measure with the Breyer score of a non-informative model. So what is the non-informative model? The non-informative model does not give me individualized predictions, it gives everybody the same prediction. It's the mean probability of the outcome. So if I have 30% mortality, it will give me the first patient or 30%, the second patient 30%, regardless of their variables. That's why it's called the non-informative model. So what's the idea by comparing this to this? Let's see. So trust me, this is the Breyer score of our model divided by the Breyer score of this model, because I can divide here by n, right? And the other one by n, but it's not needed because I have to, at the end, I can, so if you like to call it Breyer score of our model is by n, and here I divide by n for the new one, but then I can just cancel out. Okay, so what do I hope? I hope that my model will have much less error. So I hope that this is 0. So suppose my model is as bad as this reference model. This proportion will be 1. So what we define, this R squared or Breyer skill score, is 1 minus this difference in terms of division. If my model is as bad as the reference model, this will be 1. 1 minus 1 is 0. So we can interpret the Breyer skill score as the proportion of improvement over the reference model. The maximum that I can receive is 1. If my model is perfect, I'll have, my Breyer score will be 0. 0 divided by something is 0. It'd be 1 minus 0. It would be 1. So it goes between 0 and 1. And actually, I have even cases where the new model was worse than the reference model, and then you get a negative number, which is, of course, you hope not to get that, but it is possible. Any questions about the Breyer skill score? Okay. Observations. So let's go back to these properties of non-strictly proper and strictly proper. It turns out that the Breyer score and the R squared, asymptomatically, they are strictly proper. You cannot fool them by playing with the probability. So they will get their best value, the least value for Breyer score, and best value for R squared is when you have the true probabilities. So this is a very nice property of the scores. And AUC and NRI and R squared have intuitive meaning. So this is the proportion of improvement. The Breyer score itself it has a meaning of error, but it's not so intuitive. Okay, another nice thing about this Breyer score is that it has different decompositions. you can decompose it. One of the decomposition is that it's a measure of calibration plus discrimination that we talked about. That's why I usually, in the papers, I also, aside from the, or in addition to the AUC and the precision recall area, I like also to mention the Breyer score and sometimes also the skill score. And Breyer has this decomposition to calibration, discrimination. There are also a decomposition to 3 parts. We will not go into that. But remember that it's a nice mix between these two. Okay, now I'm going to have a series, and I think this is important that if we understand this, because from now on, every time you build a model, you will be equipped with directly seeing what's happening by just looking at some concepts. So I'm going to use the calibration graph, and I'm going to look at different aspects that I can add to it. So let's start with this. So this model, so what are we talking about? At the x-axis, I have my predicted probabilities, right? So 10%, 20%, till 100%. At the y-axis, I have the proportion of the true outcome. So, and what are these circles? These circles are indicative of how many patients I have in every circle. So the bigger circle says I have many patients, and here I have very little patients. So for example, for patients with very high probability to die, I have a big group of them, right? But here I have very few patients with probability around 50%. So it's just showing me the density. So let's look at this. What is this model? If you fit such a model, the first thing you look is it is on the diagonal line, x is equal to y. So that's good. That's excellent calibration, right? Because if I say that the patient has 80% chance to die, from all those who have this probability, let's say I have 100 patients. For this 100, I said you have 80% to die. And then 80% indeed had the event. So I'm perfectly calibrated, excellent calibration. A range is how much do my probability spread from 0 to 100, if we talk about percentage. So I hope that the model has a high range. I work with models that is like predicting if a couple want a child, if the IVF procedure will work or not. It's like 30% maximum. So in those cases, this very rare events or a very small data sets, or you can get very low probabilities. So in this case, we have a very good range from 0 to 100, and there's something new. It's called look what's happening is what we call sharp. I'm pushing patients to be at the extremes of 0 and 1. So I'm pushing them to go to not stay around 50%. So most of my patients are pushed to 80, 90, 100%, or 0, 20, and so percent. So this is a good property. Now, the first thing you might think, isn't that discrimination? No, because sharpness does not mean that I'm pushing them correctly. It could be that I'm saying that all those who died, I say you will live, and all those who lived, I will say you will die. Extremely bad discrimination, extremely bad model, but I'm 100% sharp. So it's just the tendency of the model to be bold, to say 1 or 0, to push them. But in combination with other things, sharpness can be very useful. Let's look at how we can measure this sharpness. So it's a simple measure. You can just look at, so for every patient, you look at the prediction of being 1 and being 0. It's 1 minus. So just take the prediction. It's a measure of variance, right? So you just look how much. So if all your the predictors are 0 or 1, this term is always 0, right? So it's either 0 multiplied by something, or 1 minus 1, which is 0 multiplied by something. It's an unsharpness. So you will be maximum sharp if this is close to 0. Okay, so that's a measure. It's not so important. The concepts are more important than how you measure them, but you can look at the slides later if you want to use this measure. And actually we use sharpness in one paper of AIME, that's coming up on I think Thursday. And we just use sharpness to see if models are tending to go towards the global mean or not. Okay, let's look at another model. So I'll be happy if you, in the future, just look at these things and you have this concept directly applicable to you. So this is excellent calibration. There's no question about it. You see all the predictions are on the y is equal to x. But now it's poor sharpness because look at the patients. Most of them I'm predicting around the middle, and very few are pushed toward the 10 and 0, 100% and 0. This is a model which had poor calibration. So for example, if I say 80% probability, it is 70 in practice. And so it's not well calibrated, but it's very sharp. It's pushing patient to the zeros and ones. So, and usually you will see like in engineering, it's trading off all kinds of things. You want sharp, but then you lose a little bit on calibration. You try to improve calibration, you lose on discrimination. And so we are an engineer in that sense. We need to find a good balance. And this one, what is this? What do you think? Is this a sharp model? It's a question to the audience. Just to
No.
make sure you're not all sleeping.
No.
No, it's not sharp indeed, because the both are here. And Silvana, is it well calibrated?
Oof,
The line should go here, eh? I'll because I didn't.
Not perfectly.
No, but it's going from 10, eh?
Yeah.
So actually, let me show you this. It's a trick question, of course. Eh? Is it work? Okay.
Oh,
Okay. So it should work from here, from 0 to 1.
Mm-hmm.
So it's not well calibrated because it is on a line, but this line is not the diagonal from 0 to 100. So, and this one, okay. And then I want to add another thing called resolution, and I promise you then to slow down because now we have a lot of concept that we learned. I'm going to use a resolution to add it. So range we know from 0 to how much, or from where's the range of probabilities. The sharpness is pushing around the edges. Calibration, we know what that is. And now I'm going to add resolution. And resolution is the tendency of the model to push you away from the mean. So let me show you this. This is one model, which is bad resolution. It's not jumping much from the mean. Over the whole predictions, it's not jumping too much. And this one has a better resolution. Well, it's not well calibrated. It's just a different story. And if it's not, the range is not high, it's different, but the good resolution. So what do we do with the resolution? We'll take the different, we sweep on all the predictions, right? So I start from here and I sweep, I go on all the predicted probabilities and I measure how far are you from the mean. And I take the, from the mean, global mean, and I take the mean of that, the average of all these arrows that you take from 0 to. I'll tell you what the difference, because you can think, oh, but this is discrimination. It looks like discrimination a little bit, but you see in all these things, you can either look from the predicted probabilities or you can look from the outcomes. There are two different aspects that you can see these graphs. Am I talking about the predictions or I'm talking about the true outcomes? I'll show you the difference in the next slide between resolution and discrimination. But this is a way, this is just in a formula, what I just said, when you take the expected value of the predictions when looking at the difference between the expected value of the ones. So this is, okay, so let's just, so these points are out here on the line. And this line here down, that's exactly the difference between them is this, what you see here. And then I take average, I sweep it on all the F1. So the difference between resolution and discrimination, because they're a bit related, is the resolution is conditioned on the predictions. So I look at the predictions and then I see how far they are from the mean. Discrimination is about first taking the outcomes, taking those who lived and those who died, and then I do obtain the measure. So they are different, related but different. Okay, so maybe it's a moment, it's good to appreciate how much we have achieved up till now. We talked about discrimination, discrimination slope, the area under the curve, the net reclassification improvement. Those are the ability of the model, the measure ability of the model to give more probabilities of dying to those who died than those who lived. Calibration is about having your probabilities well calibrated, that they are corresponding to the true proportion of the event. And we look at calibration intercept and calibration, the calibration graphs, that's the most important one. And I just mentioned that there's one that takes calibration intercept slope, but did not discuss it. Then we looked at accuracy measures that combine calibration and discrimination. And specifically, we look at the Breyer score and the Breyer skill score. We look at the range, at the sharpness and resolution. Which one do you use is always dependent on what you want to what do you want to show. The problem is sometimes that people cherry pick which one they show because they think, oh, my model is very good on this one, the Breyer score, so I report only that. So there is sometimes some reporting bias. But at least the tripod that I talked about, the tripod statement, reporting statement says, at least give me a measure of discrimination and measure of calibration. I will add to that Breyer score. Okay, so now another related thing is not only well, it's a bit related to the fact that which one you choose. Sometimes you choose one because it's significant or nice. But the question you always have to ask yourself, whether the performance measure that you choose to report or obtain fits the idea of the use of the model. So let me show you. So the pitfall here is that people sometimes ignore the correct one. So let's take a moment. If you want to inform patients and their families about the chance that their loved one will survive or not in the intensive care unit, calibration is probably one of the most important things. I really need that calibration is good. Discrimination is good, but calibration should be also the leading. Why? Because if you tell me, my model says that this patient has 70% chance to die, and then you say, okay, it is too high, I'm going to stop therapy. Because people in intensive care unit usually, when they die, usually it's the decision of the doctor to say, okay, now we stop, we withdraw treatment. So if you do this decision based on a model which is not calibrated, so you later, because you did the tutorial, you're going to try you do the calibration, say, oh, but when it says 70%, it was actually 40%. It's not well calibrated. Then you have a problem. So calibration is important. There's also examples of what we call benchmarking. When we compare different units with each other, calibration is extremely important. Sometimes calibration less important. For example, if you are the government or the municipality and you say, okay, I have a budget of $1 million or €1 million, and I want to dedicate them to the highest risk patients to develop something, or highest, if in public health or whatever. In that case, discrimination is the most important thing. Why? Because for me, the predictions are not very important as long as the order is good. So I'll take, for example, the top 25% more at risk. That's fine, even if the probabilities are not well calibrated. I know that they are the highest probabilities. So be aware of this point, like which measure you use and for what practical application you need it. Okay, so let's take a, okay. So now it's time to wrap up. So let me just talk about valuable. So remember the Murphy framework, I think maybe I have it here, where we talked about consistency. You say what you believe. Quality is all the things that we're taking today is the quality, statistical quality, and one is about value. And value is in the context. Is it adding something? Are you preventing deaths? Are you spending less money? Are you more efficient? All these things is why we use it. So remember that when we talk about evaluation of models, we are focusing on the quality part, but value is an important one of them. And factors affect it. So if you make a nice model and nobody uses it, well, the effect is nothing. So what are factors that we look at when we think about, so somebody wants to sell you a model. So some things you have to think about: the quality of the model. Did you have a large, high quality data set? Did you use a study protocol with sound statistical analysis? Did you validate it well? We'll talk about validation later. But also usefulness of the model. So first, I need to have some trust that it is statistically okay. But other factors that are affecting my use is it useful? Do I, for example, some prediction models, they will require something you don't have it at the time. In the emergency room, it's asking me about some lab result, but I mean, I need to wait maybe 6 hours to get it. So it's important. Another thing which is also useful, if it doesn't have to be, prediction models don't have to be causal at all, but it would, I'd be happy to see causal predictors in your model. It gives me more trust. If I understand the predictors, it helps to use it. Complexity and format and ease of use in a consulting room is important. Does it only give me a probability, or does it guide me? Like if it guides me, telling me, okay, the probability is 60%, and it's like a decision support system, and I suggest that you consult with or refer the patient, then it will be more useful model. And one thing which is medicine we should be also aware of: endorsement. If somebody very, like opinion leader says, yeah, this is a great model, then maybe people will use it more because they trust that person. Okay, so I suggest now we take a break. We do the same thing. No, I give you more time. In 16 minutes, so quarter past, whatever your time is. Yeah, so see you then.
Okay.
Except if somebody has a question at this moment, it's also okay to spend 2 minutes on it.
Just one, I mean, what do you mean by unambiguous predictors?
Okay, that there are, so if you say, I'm using high blood pressure is my predictor.
Okay.
So with for you it's 140, for me it's 160. That's, yeah. And people sometimes use, especially, for example, intensive care, there's the Glasgow Coma scale. You have scales that are really subjective, that you look at the patient and you say, I think they are responsive. So if it's ambiguous, if you score it differently than me, people are a little bit reluctant to use it. But if it's really like it's blood pressure and not high blood pressure, but blood pressure, then it's an objective unambiguous.
Could I ask one question more before we move on, please? When you are using artificial neural networks for a binary outcome, is the value of the output neurons that it provides a probability, or how do you treat it when you are calculating calibrations?
Yes, so if it's a sigmoid outcome activation function, it's by definition you can treat it as a probability. Okay. If it's not, if it's a linear or a ReLU, it's not a probability. But if what we do, for example, you could take outcomes, for example, from SVM and just put them in a sigmoid, you force them to become probabilities.
So you force the output layer through a sigmoid again? Yes.
So you will see if predictions are about or softmax. So if you want probabilities, you will see a sigmoid at the end.
Yeah.
And for calibration, you have to do the same thing that we did. If it's a probability, you just compare it to the proportions of events in your test set.
Okay, but you must have a probability before you move on to calibration.
You mean that first you have to calculate the probabilities first? Yes, because otherwise, of course, you have also calibrations. If it's we are only talking about 0 and 1 binary outcomes now. But if you're predicting a continuous value, calibration will be that the mean. So it will be that the prediction will be the same, but the proportion, it will not be proportional. It will be the mean of the outcomes of the test set. So you can still talk about calibration, but my calibration for today is only about binary outcomes, but most of them can be generalized.
Okay. All right. Thank you very much.
Sure. Any more questions before? Okay, so meet you at 1:15. I hope it's not too daunting a task to follow a tutorial so long. So we will keep some time for questions, and I encourage you to stop me when you want. So my first question now is whether you have any questions up till now in terms of performance measures, how to obtain them, before we go to the next subject of how to use these performance measures in model selection and validation. Any questions about prediction models, whether prognostic or diagnostic? No? Okay, but feel free always to stop me and ask. We can have a discussion. Okay, so we have covered now two parts. The introduction, what are prediction models, where they're used. We covered the performance measures, and now we see how we use them. One important topic is model selection, and the other is how to validate the models. And by validation, I mean getting an honest estimate of how well they perform on unseen data sets. So let's go back to the life cycle. And we talked about, let me just go first here. We saw that performance measures play a role in building the model and in validating it. But I haven't shown you exactly how, I just defined them. So let's see how we use them in building a model. And the important concept here is model selection. So what is model selection? So when you build a model, you will see, because then you are an engineer, you're trying to find a good model, that you have different choices about the complexity of the model. If you are fitting decision trees, you have choices about how large they could be. So you have a choice between small trees and large ones. If you are using neural networks, deep learning, how many layers, how many neurons per layer, and so forth. But even in regression, of course, regression models, we sometimes want to select the covariates that are most important. So how do we do this task? You could say, well, you know what, let me give me the most complex model, and that's it, because, well, then I can predict everything. Why should I, it sounds like strange to have to choose. Well, the problem is what we call the bias variance trade-off. And I assume most of you, or many of you, are familiar with it. But allow me to present it anyways, for those who haven't seen it before. So what's the bias variance trade-off? Now, when you build a model, let's introduce it by procedure. So I give you a data set and you start fitting a model on it. And what you do during the fitting is allowing it to go more in complexity. So for example, you're adding more nodes to the decision tree, or more neurons in your neural network, or more variables in your regression model. It could be also different terms. You could have one variable, age, but you can add age square and age to the power 3 and so forth. So do you need to use the cubed age, age cube or not? Well, so what happens if you do that, if you make the complexity higher and you have here some measure of error. So if, for example, if you use the AUC, we talk about 1 minus the AUC, right? So it's a measure of error. You will see that your model will go from some error and just going to reduce it. It's going to be better and better on your own training set. So if you test it on the same training set, of course, you will get a better result. And at a moment, you cannot, you just have two patients with the same characteristic, different outcomes. You cannot do better than that, but you can reduce it a lot. Now, the point is that if I keep a test set that you haven't seen, your model haven't seen, and I ask you every time that you build a model, for example, with one node, I also test it with my test set. Suppose the big test set, or it's representative of the true error. So I will see that it is gone also to let me just go back. It will go down. So that's good. So your model is getting more complex, and indeed the error on your training set is getting better, and also on mine. So it's getting lower. At a certain moment here, around here, you think, okay, I'm doing well, and you're continuing down. And in my case, my error suddenly goes up. And this is exactly the concept of the overfitting, right? My model is becoming too complex. So what is happening here is on the right-hand side, it is too complex. It's becoming too variant. We'll talk about the bias variant soon, but the phenomenon is there that model complexity should be optimized. You should not go for the highest, and probably also not for the lowest complexity. The truth is somewhere out there in between. And the difference between the true error and the ones that you're measuring on your own training set, we call optimism. So that's a difference in the error. It's called optimism because you think you are here, but actually you're here. So it's the distance between the truth of what you think. Okay, so models that operate in this region will be high bias models, but low variance. And models in this area will be low bias and high variance. So what does this mean? High bias means that you're far from the truth. So your estimates or your predictions are far from the real thing that I want to find. So the betas of your model are a bit incorrect. The model is too simplistic, but the good thing about it is that if you get a training set and you fit it again, you get about the same results. So your variance is not so, one day you give me an answer, the next day you will still lie to me a little bit, but it's about the same estimate. You're not going from one answer to a completely different one. These models here that are very overly complex, they have low bias in the sense that on average, they're telling you the truth on average, but every day they give you an answer. It can be very different. So you don't know if to trust them. They give you an answer now. I know that on average, you're telling me. So if I ask you with a data set and give you another data set, I can take average and I will find the truth. But in general, when you give me estimates, I don't know if to trust you or not. So here is the game that I just described. So for you, I'll give you a test set. Sorry, I will measure your performance on test set. Every time I give you a new training set and tell you, make your model. And these models, the high bias, low variance, are in general far from the truth. So the bull's eye here in red. So your estimates are far, but on every sample, you are about the same place. So you're biased because you're far, but you are not variant because all your answers are close to each other. If I do this with a very complex model, I will see that I'm all over the place. Every time I give you a new sample, you give me different estimates. But on average, it's fine, So I need somewhere in the middle that I reduce the variability by becoming a little bit less complex, but also improving my bias by giving it a bit more complex. Making some models here should become a bit more complex to get these points a little bit in the middle. What is happening when these points become a little bit close to the middle, they become also wider. So somewhere I have to stop. So that is a little bit variability, but still I'm close to the truth. And if you look at models that we all know, where are they in the spectrum that I just described? So if we look at supervised learning approaches, you have the parametric statistical models where you give me a pre-specified model. You tell me this is a logistic regression. That's it. It's beta 0 plus beta 1 multiplied by age. This is the linear predictor, and you can plug it in the sigmoid, the logistic function, to get the probability, but that's it. I can just fit this beta 0 and beta 1. when we talk about statistical machine learning techniques, we mean that there are more non-parametric. I don't tell you beforehand how many layers of neural network should be, how many splits should be in the tree, and so forth. And well, we could even go further to deep learning, where you have many layers, and each layer tries to capitalize on something in the data. So models here in this area, parametric tests lie here in the spectrum. There are more high bias, low variance. So linear model, logistic regression, Cox regression are here. And the non-parametric models, decision trees, deep neural networks, and neural networks in general, they are more here if you don't take care. So these are prone to overfitting, and these to underfitting. So we would like to hit this point. So how do we find this point? Because above it, it is I'm overfitting, and under it is an underfitting. So here, I'm not listening enough to my data, and here I'm listening too much to it. Okay, so there are two lessons that are very important to this part. One is that we need to control for model complexity. I think you've seen why. And the other one is that you cannot trust performance on the training set. And I'm going to deal with them separately. So first, how to control for model complexity. So keep in mind how I'm going to get an honest measure. We will leave it for later. I just now want to focus on having the right complexity of the model. So there are different ways to do it. And of course, hoping that I'm not overfitting. So one approach is using the AIME information criterion. Ridge regression and lasso, all these approaches play with the notion of giving penalty to the likelihood of the model. So so when the model becomes more complex, they give you penalty because they try to balance the expressiveness of the model and the penalty that goes with it. Or I could use cross-validation. There are also other approaches. We'll talk about these in this order. And then we will gonna see that we cannot trust we've seen that we cannot trust this the performance on the training set, and we must find a way to give an honest estimate, but you hope that you don't lose too much data. So we could do that by something called cross-validation or bootstrapping. Now, you probably noticed that cross-validation is mentioned in both of them. And indeed, there's a way to do nested cross-validation where you take care of the complexity and have an honest bias at the same time. So let's briefly talk about the measures of controlling the complexity of the model. So we can adjust for it by using the AIC, the shrinkage, or lasso, or use independent observation, like I will show you how by split sample or cross-validation. So let's look at the AIC, AIME information criterion. So the AIC is basically a measure of the log likelihood. It's a log likelihood, something you would like to increase. It's good, but when multiplied by -2, there are different reasons why, but basically it becomes a measure of error. And if we don't take care and we just optimize the -2 log likelihood, our error would just go down, down. So somewhere we have to stop. And the way the AIC does that is just by adding penalty. It adds error, and the error is just 2 times the number of parameters you are estimating. So if you have more nodes in the tree, I'm going to give you more penalty. So on the one hand, you're going down, you're going better if you're going high, but at a certain moment, your benefit of going from one complexity to the other is so small that my penalty is too large for you and you have to stop. So that's a nice way to do it without having a separate test set or other data set to control complexity. So it tries to find this sweet spot where to stop. And it's useful for model selection, this approach. And it works for regression models and comes with different variants. But the idea is simple. The other approaches, shrinkages and ridge and lasso, they are applying shrinkage to the estimates. So the idea is simple. if you're going to build a model, I'm going to give you a budget for your coefficients. So the ridge regression says if your coefficients altogether, you know, they should be constant. In the sum of your squared of the coefficient should be constant. So you cannot have, for example, if you're fitting a linear model and you get one of the coefficients like 12, maybe it's too big. So, and we know that if you, when you overfit, you will see, I don't know if you've looked at models when you try to overfit them, if they're regression models, you see that coefficients getting crazy because one will be very, very large and then something compensates for it where there's other terms. So if you look at it, some of the coefficients will be large. So by saying, no, no, you cannot go so large because I gave you a budget for the sum of the squared of the coefficients, then you have to stay in a family of models that are well behaving in that sense. Now, lasso is the same kind of idea, but instead of the squares of the coefficients, I tell you the absolute value of them should be constant. And the nice thing of this is that when you do the lasso, it tries to shrink these coefficients, but at certain moment they snap to 0. So they just snap, and there's a nice explanation for it, but it's effectively doing variable selection at the same time, because having a 0 coefficient for a variable means that you did not select it. In both cases, you have to say what your constant is, you know. So there's a hyperparameter for it, but the idea is simple, right? So in all these, the AIC and the ridge and lasso, you are controlling complexity by saying, I give you a budget or I give you a penalty, and this way you keep the models manageable. Another idea, which is actually much simpler conceptually, is to say, well, you know what, the truth is in the data. So let's look at the performance on a split sample. So we split the data and we look at the sample we held out, and we just look at the performance and stop when we want. So let's see how we do that. So first, just to remind you what cross-validation does, or in this case, split sample. You have a training set, you have a test set. So you start with a big data set and you split it, sometimes 2/3, 1/3, it's common. You fit the model here and you test it here. And you can do it with cross-validation. It's just a generalization of the idea. You cut it in k folds, usually 10 or 5. And you fit the model on k-1 folds, and you test on the last one. So this gives you an estimate of the error. But what we want to use them now is not for finding the error, but selecting model complexity. So you could use the same idea. You say, you know what, I'm going to train my model here. I can show you it's much easier here with an example. So I'm going to take a data set. So you gave me 100 patients. I kept 20 patients or 30 patients for the test. And now on your training set, you're going to build increasingly more complex models. So here I have just one node, it's basically the mean of the outcome. And then I have here 2 splits, and I have more splits and more complex models. And you're testing on your test set. So you see the error here, it's going down, down, down. Oops, it went up. So it's exactly the idea that we had before when we introduced the bias variance trade-off. And I say, okay, this is the moment that I should stop, right? So you could say, this is what I need. And you can now say, okay, fit. So you go back to your data set now, and you're allowed to fit on the whole data set, if you want, the complexity that you found here. For example, the complexity is 1, 2, 3, 4, 5, 6. I have 6 splits. So you go back to the data set, all of it, the 100 patients, and you say, now build the tree. It doesn't have to be the same as this one, but it has to have 6, maximum 6 splits. And then that's your final model. So this idea, you can also do it for cross-validation, and we can show it here. Now I have 10, for every time I enlarge the complexity, right? I have now 10 results, because every set can be one time in the test set as a test set. So I have 10 test sets, so I have 10 results, and I look at their mean. So now this is a better estimate than just have one-time split, because now with cross-validation I have a mean, it's more stable. So still here, if you with our eyes try to find the mean here, 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 again, it's here. So I can take this one, I say, okay, this is the best complexity. Use it, go back to the whole data set and fit with that complexity. So you still use the whole data set at the end, but you use this trick of using test set for finding the complexity. There is a problem with that if you don't take care. So let me just reiterate what we just did is when we just wanted to build a model, and I showed you how to find the final model. But it's tricky to say, oh, I found the final model and I have the right validation for the right, I obtained the right performance measure, the honest ones. Let me show you what I mean by that, because now we talk about validation. So let's go back for a second and see something subtle, but often done in machine learning, which is incorrect. So when you are finding the best complexity, right? I'm including here, increasing my complexity on the x-axis, and every time seeing on the test set that I kept apart, right? It's going down, it could be cross-validation, doesn't matter. And I hit this sweet spot to say I have to stop here, right? So it's 6 splits. I can go to my model, which looks like this. So it's a bit different than this one, but it's also 6 splits. And now you can say, yeah, but I'm also finished. If somebody asks me how good is my model, yeah, how expected your performance is, you can say, well, that's it. This is the number I give you. So for example, this is the prior score or 1 minus the AUC. I can find it here, but is it? Well, there's a problem here. So for finding the final model is okay, but for telling me that this is the expected performance is not allowed, because you use all the data, including the test set, to decide where to stop. So if you use that, you cannot measure, you cannot give me this value as the performance measure. So it's a subtle point, but it just means that if you want to find the best complexity, you can use these measures, UCBRA, whatever, to hit where is the complexity, that's fine. And you can use this complexity to go back to your whole data set and fit it. You sell me the model, but you didn't sell me the label of how good it is yet. And you are not allowed to use this value that you found here. So we have a little dilemma here. How to get unbiased estimates of performance. So one approach, which is used in deep learning, when sometimes you have a lot of data, it says, you say, you know what, yeah, you know what I'm going to do? I'm going to use 3 data sets. I have so much data. I train it on a training set. I tune it on a separate set. So I look at this and I test it at the end when I'm happy here. So the tuning will decide how much the complexity should be, and I test it here. That's fine. So in other words, you find the best model, right? Because you train it on one and you tune it. And some people call it, by the way, it's a bit confusing in deep learning. They usually call it train, validate, test. I prefer the word tune, because then it's clear we're not validating in the sense of something we didn't see completely before, because I'm using it actually just to train the model. So you could do it and then you test it on the test set. That's fine if you have a lot of data. But it's costly in terms of data. And the other thing is that maybe you had a lucky day or a bad day by this split. How do I know that this is the right split? If it's a good representative. And I even seen people doing this thing until the result is good and then they report it. So that's really wrong, because of course I can find a strange test set where I do very well on it. So there's actually even a reporting bias that people maybe would try it until they have a good result, and then they say we randomly. No, it's not randomly anymore. Okay, so another better way, if you can afford it. I mean, this is in NLP approaches and stuff. Sometimes the only thing you can do, because it is so costly to train a model that can take weeks to train. And then you cannot do these other approaches like cross-validation, bootstrapping. They will take so much time. But if you can spare, if you can do something for, let's say, 100 times, I will go for nested cross-validation, which I'll explain next, or use bootstrapping. This is if you can do something thousands of times. So in any case here, by the way, you can also go back and fit your final model based on the whole data set. My point is, for fitting the final model, you use everything you can lay your hand on, all the data. But for telling how honest it is, you either have a completely fresh test set after you've fitted the model and you're happy with it, with the complexity you found, or you have to do something that I'm going to talk about, the nested cross-validation or bootstrapping. Any questions up till now? Yeah. No? Okay. So now we're going for the cross-validation. We're going to use it in a nested way. So first I do a normal cross-validation. I mean, I split my, arrange my data by having 10 data sets. Every time I have a different test set. So if it's 10 cross-validation, I'll have 10 test sets, the same data. Every time I use a part for training, and then I have this outer loop will be used for the honest estimate of my performance. This is the test, real test. But inside, I adjust for complexity because I still need to have some data to allow me to say when to stop. I'm not using the AIC or the lots, or I'm using feedback from another external test set for me, in a way, just to tune the model. So inside this, the internal loop will be used also cross-validation. So I'll have here cross-validation again in this side, and it is used. So I'll do 10 times cross-validation just to decide on the model complexity. So I'll train on all but one and test on the one left. And so every one of these small data sets will be used for finding where to stop the complexity. And then I have a mean complexity, and I say, okay, I have a mean complexity here. I'll fit it on this data set inside, and I test on this one. I know it's a bit complex, but if you do it now, you repeat it for all these ones, what you've achieved is that in the internal loop, in the inner loop with cross-validation, you are working on the finding the best complexity, but then you test on this one. So these tests at the end, these 10 tests, I average them, and this is what I sell you. This is the performance I expect. But the final model, you're allowed to put them all together at the end, all the data set, and take the mean complexity of all the mean complexities, and then apply it to the whole data set. So you sell me a model based on all the data, and you sell me its performance based on this approach that you did something with it, like you tested it with cross-validation. It might be complex now, but maybe if you take time and read it offline, that it makes sense. But I think the concept is clear. For testing, we always need, for honest estimate of the performance, we always need to make sure we didn't use that part of the data for doing anything with the model. The other approach is bootstrapping, and I can go, it's easier to explain it with procedure, graphical way. So suppose somebody gave you a data set. Now, let me just move this bar. Okay. So, and I fit a model on it, right? So I did my logistic regression or neural network. I have the model. Now, I test it on itself, which I know it's not a good estimate for honest. It's not an honest estimate, but bear with me. So I get the performance on the data set. It can be the AUC, the Breyer score, the sharpness, whatever you want to measure. Now, I want to correct this. I know that this is not honest because I tested on the same. So what I'm going to do, I'm going to make 1,000 bootstrap samples. What's a bootstrap sample? Bootstrap sample is just I take the original data set and I draw, but with replacement, 1,000 patients. So if it was 1,000, I will still have 1,000 here. But the difference is now with the original one is that some patients will be selected 10 times, some will be not selected at all, some will be selected only 3 times, and so forth. So here there will be replication. And I do it 1,000 times. So these, all of them, they look a little bit like the original data set because they have, so every patient here in the bootstrap is also in the original, but some are more than 1 time and some are not at all. the simplest approach to bootstrapping, there are different variants, is to say, okay, now I have these bootstrap samples. What I'm going to do, I'm going to mimic what I've done here. I'm going to make a model on the bootstrap sample. So I have 1,000 models, and I'm going to test it on itself. So in a way, I'm mimicking this idea of testing on myself, which I know is not a good idea, but I need to correct this estimate. Now I have 1,000 performance measures on the bootstrap samples. Now we make it a bit, but not too much, a bit more complicated. We're going to apply this model not only on its data set where it was learned, but also on the original data set. So in a way, this original data set is a kind of external data set for it. And it turns out that if you take the difference between, so the performance on yourself minus the performance on the data set, right? So for example, this is the AUC. The AUC on yourself will be probably higher than the AUC on a different data set, although related, but different. If you take all these differences and you take their mean, it's the optimism that you expect. So this, if you take the mean of these differences, it gives you a measure of how much you are off when you did this. So when we did the performance here, let me take the pen. So did it work? Yeah. So this performance, I know it's biased. I know it's a bit too much, you know, it's not honest. But I say, okay, here I looked at how much off I am, how much mistaken I could be. I take all these differences, the 1,000 differences, I take their mean, and this is exactly what I'm missing, how much I am, this is my optimism. So I go back to this one. I say, okay, I know you're a good starting point, but I don't trust you completely. So I'm not going to take away from you the optimism. So if you got an AUC of 0.78, maybe on the original data set, maybe the optimism is 0.03. And then you report the bias corrected estimate of the AUC is 0.75. Okay, so this is a very powerful idea. The problem with, of course, with this is that you cannot do it with deep learning, where it can take a lot of time. It's very intensive. Okay. Oh, I'm still in the pen modus. Let me go back. Yeah. Okay. I'm still back in the pen. Yeah. No. So note on bootstrapping, we did not use it to choose complexity. I didn't show any place where you could use, but what I do here, it's an honest estimate. So if you do something, if you have a strategy to build models, right, you can do bootstrapping to give you an honest estimate. It does not help you to select the right model. It just helps you to obtain an honest estimate of the performance. So you could do, this can be very crazy, this M, the model. It could already control for model complexity. It can have missing value treatment. It can be anything. If you repeat it here this way that I showed you, you will get an honest estimate. But you should take care of the model and model complexity in your strategy itself. Okay, so this is an important point. If you're going to do, and I've seen also mistakes done when people using Bootstrap, you should not touch anything. So all your strategy should be repeated. So if you have multiple imputation, if you do variable selection, if you do multiple multiple basic values, variable select, anything you do to the model, deciding on threshold, deciding on hyperparameters should be repeated completely. So repeat S in each cross-validation or bootstrap sample. And actually, when people say, I validated the model, usually what we mean by that is we validated the model building strategy and not the model itself, because you didn't sell me a model, you sold me an approach, and I repeat it and I see what's expected error from it or expected performance. And this is an important point. We are validating all the time strategies of building the model. So here, the same thing, you do the strategy in all of these things, repeating anything you've done of it. This may be a good point to ask if you have questions. Is it a bit clear, the idea? So let's go back just for a second here. I just want to bring a point. Let me see. Okay, so for controlling informatic complexity, you do all your best, whether you do cross-validation, split sample, or any of these, just to know how much the complexity should be, and you use all the data at the end, all the data to finalize your model. If you want to sell me this model and you tell me what's performance, you have to do something. I don't trust it if it was based, even the selection of the model based on the test set, I don't trust it. So we have to do these approaches, which can't go in tandem with the other one, like nested cross-validation gives you both answers at the same time. But you have to be aware that the final model has to be, or the strategy to build the model has to be validated by doing it in one of these approaches, either having a completely fresh test set, doing cross-validation, or bootstrapping. Okay, so now let's go to forms of validations, the different types. Okay, so yeah. So type of validity. There are three types, large parts of to validate them, ways to types of validity. One is the internal validity. So up till now, implicitly, I was talking about internal validity. You do cross-validation, you work with the same data, but you have to make sure that when you test, when you validate the model, you don't touch the testing data for building the model and for reporting on the performance. Now, there is another way. It's temporal or temporal, depends how you want to call it. It's prospective validity, where you look to say, okay, now I built the model, I'm going to freeze it. That's it. Now, it's different than this one, because internal validity, I'm validating the whole strategy. I'm repeating it just to see how good the strategy is. And here, it's a model. You've done it, you fixed it, and now you're going to look at future patients. So your model, you built it from 2015 to 2020. You publish the model, you know what it is, and now you're waiting for new patients, and then you're going to test it on future patients. And this is important because this mimics how the model should work in practice. So if you use very old data, I really want to see what happens when you test it on new patients. External validity is when you test it on a different population. So it could be a different geographic part. It could be you test it on adult patients and you're trying on a mix between adults and children. So it's external. You have a different population that you expect, different setting. Let me give you an example of external validity. I'll just show you because you can read the slide about the details. But we have a model that has been published. I think it is NEGM or yeah. So NEGM, the New England Journal of Medicine, is a very well-respected journal, and there was a paper about the model that was fit in one setting here. So this was the original value of the. So these are the original values of sensitivity and specificity, and the AUC was very high. You see, it's a very nice curve. The area is very high under it. But when other researchers tried it in a different setting, it was about half. So half, AUC of half, it means that you cannot discriminate between the classes. So this is a dramatic drop in performance in a different setting. It could be that the model was too complex, too specific, or the population is very, very different. So it could be either a methodological problem or that the population are so large, but I think it must be a mix if you get such a drop in performance. Let me see, what time is it now? Okay, so maybe we take 5 minutes, finish this, and then we go for the break. Interpreting external validation. So when we talk about external validation, it's sometimes good to think, why did my model do differently in the new setting? What could have been the reason? So there's a framework of Debray. It is a nice framework where it tries to give you some insight about the differences. The internal validation, the AUC was 0.75, and then in the new setting it was 0.6. What happened? So one way to look at it, it's a simple idea. So here you build what we call a membership model. So what you do, you take, but you can only use this approach if you have all the data set of the original data and the external. So what you would do, you would take the original data set and you stack the new one on top of it. Let me see if I can. So here, this is the original data set. This is original. And I'm going to stack on top of it the external data set. This is external. And I'm going to add a variable, a column, which I'll call the class. So this is the member, it's the class. So this is the new class. So in the class, for all the external patients, I'll add 1, right? And for all the original, I call them 0. And now I'm trying to predict. So it's a prediction model, if you like, meta prediction model. Give me the characteristics of your patients. So age, sex, and all these other variables. I'm going to use them to try to predict if they are in the external or original data set. So what happens if the external data set is very much like the original one? There's no distinction between them. If there's no distinction, this model that I fit, the membership model, if I can predict where you come from, external or original, the AUC will be about half, right? Because there's no difference between them. If, however, the external data set is very different, and very much older patients, and most of them are males instead of the other one. So if it's different, when I try to predict, I think, oh, well, just give me a patient. In general, I can predict this old and male is probably in the external one. So the AUC will be high. And this is what you see here. This is the AUC of this model, not the original models, but it is of the membership model. Can I predict where you came from, the external or the original one? So the original study will be here, this original study, because it is AUC is half. It's the same kind of as myself, my own population. I cannot predict, cannot make distinction between my data set and my data set. And here, it's a measure of spread of the difference in spread of the predictions. You know, like if one, my original model was 0.1, we just take 2, 4 patients, 0.1, 0.2, 0.3, and 0.4. And the other model was, for example, 0.05 and 0.1, 0.4, 2, 3, 4. Okay, and then 0.7. You see the spread is higher in this model. So this is trying to quantify the spread between these two. And LP stands for linear predictor, but it doesn't matter. The idea is how much is spread. So for example, if you look at this study, new study, you have a new study means I have a new data set here, external one. And I plot it here, and I have some measures of error bars. It doesn't matter, the confidence around it. But the AUC is relatively high, which means, okay, what do I learn from this? I learn from this that external is different from original, because I could fairly well discriminate between the two groups. And here there is a difference in spread between the, so the spread of there is a difference between the two. If I take the two sets of predictions, the spread between them is not the same. Here's even easier. I have here the same study. So you see here, the same study here, I plotted in a bit different kind of plot figure. Here I have the same AUC as the other one, because it is the same. But here I put it here on the x-axis, I plot, so original studies here again. And here I plot, well, what is the difference in means in the linear predictors, or if you like, you can plot the difference between mean predictions. So here you see that the difference between the mean predictions, so it's it also tells you there are different populations, and also probably because one of the groups is less severely ill, or there's a different characteristics that it makes it more likely that the new model has less. So the new model here, because I see it's a negative number, but it depends how you want to interpret. But basically, there's a different risk between total risk between the external and the original. So DRV stands for derivation. Okay, but the idea is actually quite simple. Why are these differences? And this helps you to decide whether what we call, okay, I'm still stuck in the pen mode. Yeah. So is it reproducibility or is it transportability? Reproducibility means that, for example, in your data set, it was 0.8, the AUC, and in the new one, it was 0.8. So how do you interpret it? One thing to say, oh, it's a reproducibility, because I look at this, when I look at the graphs, there's no difference between the groups. So the reason that my model is doing well is just because the groups are the same. But suppose you got 0.8 and your model was somewhere here. You know, you still got the 0.8 in the real AUC, but your meta AUC is here. Think, wow, the groups are, I'm sorry, I can use the, if I'm here, this area, you say, wow, the groups are very different. And also in terms of their mean predictions. But still I'm getting a 0.8 for the model. Then you say, okay, the model is actually extrapolating, it's transporting its abilities to this new data set. Okay, so it's a tool. It's a nice tool to allow you to think what is happening when you have external validation. Okay, so I suppose we should stop now. And then I have a relatively shorter last section. It's called related topics. But I would like to ask you if you have any remarks or observations or questions at this point.
I have one, may I?
Sure.
About the nested cross-validation.
Yes.
I never heard about it. Do you normally use it, or do you use it like in specific situations, or?
Good question. I always use it in situations where I need to optimize hyperparameters of a model.
Okay.
And as long as I can, when bootstrapping, I prefer bootstrapping always, because the good thing about bootstrapping is you use the whole data all the time. Okay. I don't need to, but usually it is too much. You know, when people want to, it becomes a, then I do cross-validation, where in the internal one, I optimize the parameters, and in the external one, I optimize, I measure the honest value of the measure of the.
Okay. Because normally I use cross-validation only with the faults.
So how do you optimize the parameters?
Yeah, that's the problem.
Okay, because that could be a problem if you use the data set. So there are two things that can happen here. If you still secretly and unintentionally use the test set in a fold to optimize the model, then it is not. It will be exactly what I mentioned here.
Yeah,
you will be doing this thing. This thing here, and you will be reporting this, which is unfair because you're looking here, say, oh, where do I stop? So it is parallel to this idea. So nested cross-validations allows you to do both of them by saying, why do we do cross-validation? Because we want to control for the variability in choosing the training and test set. You know, I like cross-validation more than split sample. But the idea that you do can apply the same for split sample. If you look at the test set to decide where to stop, then this is and then you report this, then it is a mistake.
Yeah, that's true.
I have another comment. I mean,
sure.
Did I understand correctly that trying to predict about external validation, trying to predict the class, original or external, from the data, we can try to understand the causes why the model doesn't work on in the external population. For example, if the original population is mainly composed by females, no?
Yes, yes.
And I learned a model, and the external one is mainly composed by male, and I see that the model doesn't work. That can mean that the learned model is valid only for female. That can have a clinical justification, no, as a clinical basis.
Yes.
Is that?
Yes. Yeah, so that's a way to see, well, except if the model is doing very well, eh? So that would be transportable. If your model is transportable, it says, okay, it was mainly fit on females, and now you have an external data set with males, and it's still giving you good result. In that sense, you can say, okay, this framework I showed will say you, listen, there is difference between the groups, and actually, sex will be predictor of the membership class, because it will say, oh, if I know it's a female, it's very likely it is in the internal group, and if it's a male, it's very likely it's coming from the external. But if the AUC and the Breyer are still okay, you can say, well, although they're different, it's still giving good performance. So this framework I showed it tries to understand if you have differences or no differences, is how to interpret what happened. Usually you will get a different population, you know, because but the question whether it's a problem or not, it depends on the performance. It just gives you an interpretation. But if you want to, but there's another thing, Silvana, what you can do is, we had external models for predicting a procedure, heart procedure, taken from abroad. They did badly in our population, but what you can do is recalibrate them. So one simple way to recalibrate without changing all of them, you say, okay, give me your prediction, and I'm going to take your prediction and I'm going to tweak it based on my population. For example, if your population is less severely ill, you want to temper all the predictions that coming from that other model, because it's predicting everybody to have problems. So you can tweak it by a kind of meta model. So you can still say, I use the model external, but I don't like it too much. I'm going to take its predictions, and I'm going to put them as new predictors for my own to temper it, to tweak it, to make it good. So you don't have to throw it by definition if it's not good enough. Sometimes it's just a matter of calibration, bad calibration. So if you just recalibrate it a little bit, and then it has a good discrimination and maybe still in your population.
Okay, thank you.
Sure. More questions? Okay, so I suggest we take a break. It's now 10 past, so let's take at 20, so take 10 minutes, and I promise you to go quick in the last part. Yeah, I just want to keep some time if you have specific questions about your project or something at the end, then we can have some more time, and the others can do something else if you like. So we meet in 11 minutes.
Okay.
Okay. See you. Back. Just to check. Yeah. Do you hear me? Okay.
Yeah.
Yeah. Great. So let's take a moment and see where we are. So we are now in the last part, related topics. And these related topics are, I think, by definition, very subjective. And my choice is either because I found them useful, or I struggled with them initially, or I thought it's useful for this tutorial. One is important one, which I always feel when I work with clinicians. They want a prediction model. When we do the prediction model, they interpret it causally. And that's risky. That's a problem. So these two things are really different. So I'll talk about it. Then I'll talk about some statistical challenges, imbalanced data sets. We already talked about it in terms of using the precision recall. So I'll be very brief there. Population drift, and methodological reporting standards, and I'll finish with a summary. And please stop me anytime you feel you have a question. So let's take a moment and appreciate the difference between prediction and causality. So prediction is essentially about correlation, association, and causality is the etiology, explanation, like why things happen, not because they're associated by like a causal mechanism. So perhaps I can explain it by a simple, illustrate by a simple example that we did. So we looked at the question whether medically assisted reproduction is bad for the baby. So as you probably know, couples, if they try to perceive, you know, they want a child, and if it doesn't work in the first year, in 1 year, then they can, well, they are inclined to ask for help from technology. Think about IVF. So this is medically assisted reproduction. And the problem is for us, that was the information problem is whether this is causally associated with poor neonatal outcome. We will see that the babies that are born because of MAR, of medically assisted reproduction, have a bit worse outcomes. And the question is it because of technology? And I will illustrate it with something called propensity score match study. I'll keep it at a conceptual level. The most important thing for me is that you understand the difference between causality and prediction. So we looked at about 2 million pregnancies. 2.5% of them were pregnancies due to MAR, medically assisted reproduction. So technology was used. And the outcome was the UPGAR score. So the UPGAR score is a score of the health of the baby taken like 5 minutes after birth. And we saw that we categorized it, we made it simple. If it's under 4, it's between 1 and 10. If it's under 4, we called it the bad outcome. It is above 4, we called it the okay outcome. And if you do this dichotomy, you see that the babies born because of MAR, because of the technology, they have more chance to bad outcome than those who did not have MAR. So these are spontaneous pregnancies, 3.4% having, this is the bad outcome in spontaneous pregnancies, and this is in MAR and medically assisted pregnancies. And you could compare them. Is it the real difference? Yes, if you take the odds ratio, hey, I don't know if you know what the odds ratio, but basically it's above 1, and the confidence interval does not include 1. So it's if it's statistically significantly, so it's a big difference. And then the question is whether MAR is the problem. Should we stop? Should we tell couples stop using this technology, stop using IVF? So if we look at the numbers here, there's no doubt that MAR, if you ask me, is MAR a predictor of bad outcome? Yes, it is a predictor of bad outcome, because MAR is associated with bad outcome. This is bad outcome here. So there's no discussion about it. So if you are the government and you want to decide on measures to help the babies because they have bad outcome, to have them some places decide on making, you know, how to organize your health services, you could use MAR. You could say, okay, I expect next year so many, sorry, you can use MAR indeed to expect how many problems will these babies have. So you could use it as predictor. But the question here is not whether it's a predictor or whether it is the cause of it. So it could be that, can somebody say why these two things can be different, but not because they are causal? Any wild guess?
I wanted to say that the couples that use MAR are have more age maybe than those.
Yeah, excellent,
from
excellent.
The spontaneous pregnancy.
Yeah. So Bernardo is actually saying, look, this is a difference, maybe not because of the technology, but because the pregnancies are different. They belong to different kinds of couple, and perhaps, and I think so, they are older, the mother, because anyways they're waiting, right? And maybe there are other underlying health issues. And Bernardo, do you have a name for such like age? What we call it? So age, yeah.
No, I'm sorry. No, I don't.
No, okay. So age, in this case, we call it a confounding factor. Because, yeah, so it's a confounder. It is confounding the relationship between what we want to study, the exposure, and the outcome. So indeed, these two, okay. So indeed, these two groups, those who use MAR and don't use MAR, can be different, inherently different. The maternal age, the mothers could be older in the MAR group. The parity could be different. The parity is the number of the child, the first one, the second, the third. Maybe there are pre-existing diseases that already say why they cannot get pregnant. Ethnicity could be an issue, socioeconomic status, year of birth. These are variables that we call confounder. What does it mean, really, confounding? So you want to study the exposure, in our case, between MAR, so the relationship between the exposure, which is MAR, and the outcome. Outcome is a bad outcome for the baby. But confounders, all these guys, they affect both the exposure itself. Why do I go to the IVF or the MAR anyways? And my probability of the outcome. So when you study this relationship, maybe you are not measuring the causal effect of exposure on the outcome, but you're measuring the differences in the confounding factors. So in order to study this, we have to break the lines to make this confounder not active. So we have to inactivate it. And one way, there are different ways to do it. So one way is we match. So we take the MAR pregnancies, every pregnancies of MAR, I'm gonna couple it, match it with 3, you can use 5, you can use 1, pregnancies that are spontaneous. So how do I match them? They look the same as the MAR, except that they did not use IVF. So the same age of the mothers here, the same pregnancy duration, everything that you know about the mother should be matched between them. If you had information about the partner, you could also use it for the matching. But this, we had only the maternity information. Okay, so if you do that, now within every stratum of the matching stratum here, these confounding factors don't play a role anymore because they are neutralized. Because if you say, yeah, it's the age, no, but I made them the same age. If you say socioeconomic status, no, they have the same socioeconomic status. So these pregnancies pertain to the same confounding factors. And then if you look at the differences within the strata and aggregate the results, there was no difference. So the odds ratio was 0.99, and it is the 1 is included in the confidence interval, which means there's no statistical difference between these, significant statistical difference between these two groups. So the conclusion, MAR is a predictor, but MAR is not a cause. So if you want to do causal analysis, you have to take care of the confounding factors. There are more things that we have to talk about: risk factors, confounding factors. You can talk about other things. And then you are talking really about relationships between variables. And usually you need information outside the data set to decide on the confounding factors and the other variables. You can also use data to suggest, but usually you need some extra information to do the analysis. Okay, so I hope that I convinced you there's a difference between causation and prediction. And so the thing that I notice is sometimes you do a prediction model and people look at the predictors and say, oh, if I change this, then that would be changing the outcome. And actually we can talk about counterfactuals, and they have different meanings in machine learning. It means the minimum change in your variables that affect the change, that flip the outcome. But in causal reasoning, it is counterfactual is what would have happened to you if you really had the different, really changing, not by association, but by causality. Okay, so that's topic number 1. Briefly about statistical challenges. So I don't know what you do when you have missing data. Many machine learners just gross over they take the data out, but that's a bad habit. When you have missing data, you have to ask, what is the mechanism behind it? Is it missing completely at random? This is the easiest case. Or is it missing at random? Missing at random, but not completely at random, has a good solution, which is called imputation. You can use other variables to predict the predictor. So if a predictor is missing, you can predict it even, and actually you must use also the outcome to predict the missing value of a predictor. And you can do it multiple times because you use probabilistic models. So you have like 5 data sets. In each one, the variable can have of the cell that was missing can have different values according to some probabilistic rules. Okay, and MNAR are so missing not at random is the hardest part. So it is missing because of the value itself. So for example, if you ask people about the salaries, the very, very rich and the very, very poor don't want to fill it in. So you might have a missing value because of something. It's informative, but you don't know it. Correlated data is also an issue. So if I have 6 measurements of each one of us now, blood pressures, they are correlated. I cannot put all the data and use the statistical machinery, which is used for IDD analysis. So there are approaches. So in statistics, we use mixed effects models, for example, to do that. And now I've seen also in machine learning, there are also approaches that use mixed effects, even with neural networks, with other approaches, that you leave some random variable a bit free to adjust for each person or each hospital or each unit. And then within each stratum or group, you could have estimate of the effects, which are either fixed for all the others, or you can make it more flexible. Sensor data is when you have observed data until some moment and then not anymore. For example, somebody left the study, but you're measuring the time until a disease happens or until the patient dies. And in biostatistics, we use survival analysis for that. And there are some approaches now in machine learning to handle that as well. But these are challenges when you have real data that you have to have decisions on these things.
May I ask a question regarding
Yes, sure.
the last one? Things like we have a record on one patient, and like in the 80s, the guy has hypertension, but then he continues to have, but the physician stopped writing the comorbidity like hypertension.
Yes.
Can we consider that sensor data, or only the specific cases that you were talking about, like the patient drop off of the clinical trial? Or can this one, it's not a missing data, but can, because the physicians stop, they ignore the previous, like you have it for many years and I will stop writing that.
Why did they stop writing it?
Normally they stop writing because they already have it in the previous records, so they do not write in the most recent ones.
No, for me it's MNAR. So let me just try to get back here.
Yeah.
So for me, you are here in this area, and in fact, when we use intensive care data, when the Glasgow Coma Scale is missing, we assume that it's 15. So it ranges from 3 to 15. 15 is normal.
Oh, okay.
So we think they're doing it because they know they register it only when there's something wrong.
Yeah,
but this is an assumption, right? But
it's like the ones that I made. Like if you have access to all the records from one patient, like since the start until today, if the physician does not write he has hypertension, it means that the patient does not have hypertension, but you are assuming something. So that's
absolutely. Yes.
Yeah, yes. You can make that type of assumptions. Yeah, you also do that.
Yes.
Okay,
this
great.
is tricky. This is tricky.
Yeah,
I agree.
Very tricky.
Yeah, what we do usually, we do sensitivity analysis. What would have happened if we imputed them this way, or if we ignore them? How much does it change?
Yeah. Okay, thank you.
Yeah. Sure. So another problem is a prediction model is like, well, you buy a prediction model and it has sometimes a shelf life. It's not good anymore if you use it for a long time, not because it becomes worse itself, but because the population change over time, right? They're older maybe, or younger, or there's a different indication for who's allowed to do the procedure, to undergo the treatment. The technology is different. Many things can change. So what happened if to these results when prediction change over time? And actually, so sometimes you should not ignore it. You have to think about it and what happens. So we had a model that was published a long time ago. It was a decision tree, right? So I'm not going to the details, but well, we built a model. So this model here, Glasgow Coma scale, it's under 7, you do this. If it's so until 6 and it's above 7, you split the patient population. And there are some with marked with red, which means that there are really high probability of dying. There's some groups that are interesting, maybe. But the question was, okay, that was a nice model, it was published. And then later we thought, okay, what would have happened to the model? So if it was facing new patients. So that's exactly what we did. So we freeze the model. We took it as it was published, and we ran it on new patients, on intensive care patients, at a different period. And we used something called statistical process control to follow the behavior of the model. So this is the AUC of the tree. I'll not go into SPC, but SPC basically allows you, it tells you these are the ranges I think your model is allowed to change. It's not specific for AUCs or Brier scores. Actually, it's coming from industry. You could see if the amount of coffee I take from the machine is how stable it is, because maybe there's something wrong, some wheel in the machine is going wrong, and there's giving more and more coffee every time. But so this is the natural variations, and you see that the AUC stayed well inside these two ranges. We think, okay, it's stable enough. When we look at the Brier score, it was going up here, which is this is unacceptable behavior. So what's the conclusion? The conclusion is, okay, and we looked also at the high-risk groups over time, they were stable. So the conclusion is that for things like benchmarking, I didn't talk about it, but benchmarking is about is the task of comparing different units, for example, intensive care units with each other about their quality. So you have a prediction model telling you, oh, give me your patient population, and for your population, I expect so much mortality, but you have more than expected. So that's a little bit the idea. So for benchmarking, I would not use this model because Brier score has an important component of calibration and it's not stable, so I wouldn't use it. If you want to identify patients at high risk, which are the subgroups which were in red, and there are some extra ones, you could use it because it was stable. So the point I'm trying to make here is that you always have to think about the fitness for use of your model. Why do you want to use it? And especially over time, it's important to test it over time. It becomes a hard problem for the model, but they are there to guide us. So let's test them over time. And you usually see drift over time. Sometimes the performance is better than on the original data set. And why that could be happened. For example, the AUC can be better over time if your patient population, the new one, is very ill or very sick, very sick or very healthy, relatively, it's easier to discriminate between them. So it could be that by having patients now that we lose the difficult ones that are in the middle, 0.5, 0.6, we keep patients with high or low risk, then it can be that your model is becoming even better. But it's good to understand what's happening over time. Okay. So another thing that is, I think, very important in our field, and it's not really getting into the machine learning part very well, is that we have reporting standards. So when we write, there are some guidelines telling you what you should report on. So one thing, if you are using observational data. It's not interventional observation. You just look and have data. And especially if it's messy, like an electronic patient record, it's observational and retrospective and has missing values, not so nice observational that you did it prospectively. There's a record statement, which is a specific specialization of strobe. So this record statement, you can look at it, you can search for it. It tells you where to report. So if you did like data linkage between two data sets, how much did you lose in this matching? Is it maybe possible concern for bias and so forth? So this is about the data and study type. Tripod is anything about prediction models. This strobe does not have to be prediction model, but tripod is specific about prediction models. So it tells you, for example, what to report on validating models and on developing them. So it for example, says always give a measure of calibration and of discrimination. Another thing which is important, although it is meant for, so Probust is a tool that is meant for people writing systematic reviews about prediction models. But I think you can use it when you build one, because this is like, I think 20 questions that are asked about the data set, about the analysis, about the outcome definition. And it helps you understand if there are biases. And you learn a lot from it just by reading the text of the article about Probust. So I suggest that you anyways should be familiar with Tripod, and if you have more time, to look at strobe record and Probust. Summary. Excellent, on time. So we've seen in this tutorial various uses for models in public health, in the preventive sphere, clinical medicine, when people are patients, and in research, especially for including patients in clinical trials. We saw different models, parametric, non-parametric, but especially, I think point 3, we looked at various performance aspects like calibration, discrimination, sharpness, resolution, and so forth, and the performance measures that go with them. So how to perform them. So actually, I should say maybe performance aspects are calibration, discrimination, and performance specific measures could be like the slope, right? The discrimination slope and so forth. Important part was how to manage model complexity. And this is a key point for having good models. We used also performance measures to decide on this complexity. The other thing that's very important is how to measure unbiased estimates. So the estimate should be obtained by data that you haven't been using at all for building the model. So that's the reporting on unbiased estimates. The last part was about challenges and other related topic. Especially, I think it's important to be aware of two things: the causality versus prediction, and that we have standards, reporting standards. Okay, this concludes my tutorial for today. So we have time. I don't know how tired you are, but we have time for any question you have, or maybe on your own, you're working on your own paper or working on your own project. It can be specific, it can be general. So let me know if you have a question.